Yeah, I don't need lots of him. Well, thank you. So, 但是你可以这么说明的。这方法好，你去那个 email 上找那个。
I was trying to think about your question. I feel like maybe like entanglement and negativity might be a good something that like
Yeah, it's okay. Good morning, everyone. Art has given me the responsibility of sharing. So without further ado, let's get started. We have Ben Feldman from Stanford to tell us about imaging Supermoiré relaxation. I'll let you know when you have 5 minutes.
So thanks for the introduction and invitation. Today I'm going to tell you about something that rhymes with some of the talks that we heard about yesterday on Graphene, but instead of looking at Rhombohedral multi-layer, this talk is focused on what happens when we add multiple interlayer trip between Graphene sheets, looking in particular at an example of that where there's just a big direction by equal angles, and you get to kind of different time scale naturally during the problem and continue like so let me start with the most important slide highlighting the folks who were involved in the work, in particular Jesse Hoke and the graduate students and went through postdoc in my lab who collaborated on both experiments and analyzing the data. We had quite a bit of help and really great theoretical discussions with William Lehman and Dynamical, who was here and who in fact suggested this. We've been collaborating on some twisted transitional electrophotometry work, and again, some Zoom colleagues said, "Hey, by the way, I have this other thing I want to talk to you about," and it turned into this work. So kudos for the prediction, and of course we get crystals. So let me start just with a very, very broad overview of 2D materials in general. I think I don't have to say much for this audience. You can, of course, mix and match them, stack them in various different ways. And so this analogy to Lego blocks was made, and I think the analogy is in many ways apt, but actually this talk is focused on ways in which it breaks down. So one of those, as I guess I already alluded to, is these van der Waals materials that we're using have only in plane strong covalent bonds. The bonds are there are no strong bonds out of plane, and what that means is not only can you stack these things together, but also you can add an interlayer twist. And compared to other material systems, this is something which is truly fundamentally different from what you get in rocks. And you can pick up that there's this longer wavelength interference pattern coming from the eating of the two original, in this case, I guess that's usually this is two graphene lattices, but it could be anything. And because of this extra length scale, this Moiré super lattice, which is over 10 nanometers, now you have new energy scales in the problem, and you can engineer that in the system with quite a bit of practicability that isn't again available with other services. So of course, this gives rise to all sorts of fun games one can play. There's superconductivity, correlated behavior, quite a bit more that I won't go into the details of because that's not the point of this talk. Instead, I want to highlight a second thing, which actually here in Minnesota, I think is quite appreciated by several people, and also again several people in the audience have worked on some of these ideas, but. I think in the broader community, maybe is not talked about as much as it should, that because there are no strong out-of-plane covalent bonds, actually these things can, the atomic positions can shift relative to one another. So people draw these beautiful Moiré lattices that look something like this. They have different regions which may have AA stacking, carbon atoms sitting directly on top of one another, or Bernal stacking, AB or BA stacking, which is energetically preferred. And these different stacking configurations have, in fact, different energetic preferences. And since there's no out-of-plane covalent bonds, because these materials are so stretchy, you can just deform them. And so if you look in, say, TM at what this pattern really looks like, these Bernal regions, AB and BA stacking, are favorable, so they grow. and the AA stackings are energetically the least favorable, and so they shrink. And so what you get are these sort of triangular domains of different stacking widths, stacking faults between them. You can see these again in TEM imaging and various other techniques. And it's not just a structural effect. It also has, in many cases, important electronic consequences. So again, this is just an STM image of the same material system, low twist bilayer graphene. And at these boundaries, there are counterpropagating one-dimensional modes that one can actually observe. Again, you can get other things like electricity, you can topology, and so there's quite a bit of richness that comes about from this interaction between the structural and electronic. So in this talk, I want to focus not on the bilayer case, but twisted trilayer graphene that has two different interlayer angles. And this is quite a rich phase space of possible systems. I won't have time to talk about all of them, but by controlling the two different interlayer twists, you can engineer again quite different physical regime. I'll tell you about our measurement technique, scanning single electron transistor microscopy, which allows us to look at electronic properties from a thermodynamic perspective. And I'll show you actually image relaxation similar to what I showed you in the low twist ABBA graphene domains, but now at a much larger length scale of hundreds of nanometers. You can tune these sorts of features by changing the strain of the system and even learn something about the nature, again, of these boundaries. So twisted trilayer graphene starts just like this. There's a bottom, middle, and top graphene layer. What I've talked about so far is what happens when you twist two layers relative to one another. You get this Moiré periodicity, which is dictated by the interlayer twist angle. But now, as you add an additional layer to the system, you have an additional angle that you can play with. So the simplest thing you can imagine doing is just twisting and then twisting back. And in fact, this is mirror-symmetric twisted trilayer graphene. It was the first system to be proposed to be interesting by the groups of actually Nishchhal. And they showed that in fact it has analogies, magic angle twisted bilayer graphene, so these same sorts of features that one gets in magic angle bilayer flat bands are also present. So you again get superconductivity if you do a transport measurement. Correlated insulator is now tuned by an out-of-plane electric field because you have these three different layers in the system. And there's been quite a number of groups who have studied the system because it is in fact quite great. But actually, that's only one example of a case of different interlayer twist angles that you can imagine. So in general, you have some interlayer twist theta 1, 2 between, say, the lower two layers, some interlayer twist, which can be anything from the upper two layers, theta 2, 3. And there's even different kinds of twisting that you can do in these multi-layers. So you can do what I showed already, this alternating case where you twist one layer and then twist back with the last layer, or you can twist both layers in the same direction, and these correspond to what are known as the alternating and helical cases. And what I've shown you so far in kind of magic angle twisted trilayer graphene from the last slide is when you have equal but opposite interlayer twist angles. But in fact, there's quite a broad phase space. So there's quasi-crystals that you can get out if the interlayer twists are mismatched. If there's a large twist between one of the layers and the others, then actually these states are electronically decoupled because the lower energy states are at different momenta. And so you can get different systems. I won't talk about in particular any of those things. Actually, in this talk, what I'll focus on is this helical trilayer graphene case with equal layers now twisted, or equal angles with the layers twisted sequentially in the same direction. But I want to point out that in general, actually, all the way along these strips of gray here, you get flat electronic bands. And so there's quite a bit of richness to explore. One can ask the question, what new physics can you create by playing with these different tuning knobs, interlayer twist angle, interlayer coupling, structural relaxation, and so forth. And that last point is really what I'll show you today. So helical trilayer graphene, as I've already said, it comes from these 3 layers, and you twist all 3 layers in the same direction by the same angle, so you get some Moiré pattern, like I showed you before, between the bottom and middle layers. You get some other Moiré pattern between the middle and the top layers. And just as in the case where you have 2 atomic lattices twisted relative to one another to give these Moiré physics, you can imagine now stacking all 3 of these systems together. And what you find, hopefully you can sort of pick out by eye, that there's a larger, what I'll call Supermoiré wavelength. And the way you should think about this is that it comes from an interference between the 2 Moiré patterns that are present in layers. And now the length scale of this is significantly larger than the Moiré length scale. It's basically given by the Moiré length scale now divided by theta and the low twist limit, or the graphene lattice constant divided by theta squared. So this is hundreds of nanometers. So now we have a hierarchy of different length scales that are present in the problem. There's the atomic lattice, there's the Moiré super lattice, and then there is this Moiré of Moiré or Supermoiré lattice. And all of these length scales matter. And in fact, I should point out that there are other cases where Supermoiré physics is not unique to just helical trilayer graphene. It happens, for example, in the alternating trilayer graphene case, if there's slightly mismatched twist angles, and that people in Miriam Kobe's group have shown that this also has important electronic consequences, including for the interaction physics, and one can get this generically. So what's special then about helical trilayer graphene? Why am I focusing on that in this talk? The thing that is special is that, again, this same story of local stacking and energetic preferences come in. So if you think about the momentum space picture of these 3 twisted layers, what you find is that the K points for the low energy states in each graphene layer sit almost line up in a line, but not quite. So with just a tiny bit of strain, what you do if you say expand the lattice, this shrinks the Berlin zone, and so you can move by, say, stretching the middle layer slightly, this K point toward what is the gamma point sitting between the K points of the outer 2 layers. And then these things all line up together. That is, you have a commensurate lattice. This is a Moiré lattice, and locally what that gives is some stacking. So within one of these large triangular domains here, what you have are kind of AAB, ABA, BAA stacking that are represented by these different colors. So the ABA is the Bernal, that's energetically preferred. You can see there's a lot of white space here for that reason. But you also get these regions where locally you have AA stacking between adjacent layers, either the upper 2 or lower 2 layers. Those are denoted by purple and orange here in this picture. And these things break inversion symmetry. They form this honeycomb lattice with these 2 different sublattices of different stacking. And so that's what happens locally within one of these domains, which is, again, kind of hundreds of nanometers in size on the Supermoiré scale. Then as you go from one of these, say, upward-facing triangles to lower-facing triangles, the stacking order flips. So what ends up happening, if you look here, is that actually the orange and purple flip sides. And so these kind of red lines here are basically stacking faults, similar to those that I showed you in low twist bilayer graphene. So you have a pretty rich system. There are these 2 equivalent domains, I'll call H and H bar. And if you just do, so they are locally uniform. If you just ask what is the band structure within one of these domains, you get a picture that looks something like this. So there's some low energy bands near the charge neutrality point. They can be, if you have the angle right, relatively flat. They're separated by large energy gaps. In this calculation, for this angle, 100 millivolts. In real, the sample that I'll show you, it's more like 50, 60, 70 millielectron volts, but really quite substantial band gap. And because of the topology of the original graphene layers and this C2 symmetry breaking that's associated with these orange and purple spots here, actually these low energy bands have non-trivial non-zero Chern numbers. And so there are 8 bands in total. That's 2 bands times 2 spins times 2 valleys, and you can index these by an effective valley degree of freedom, a spin degree of freedom, and something akin to sublattice. Then for a given valley, And sublattice, you have a Chern number of say +1, and for the other sublattice -2. So for a given value, if you fill up all of these states per spin, actually you have a net non-zero Chern number when you live in this energy gap, and so that gives rise, I'll come back to this later, to one-dimensional boundary modes, which are predicted along these red lines here. If you flip values, this is now time reversal symmetric, so Chern numbers flip, and as if you go from one domain to the next domain, again, Chern numbers flip. So in each domain individually is a quantum Valley Hall insulator when you're in this large tens of millivolts, millielectron volts energy gap. And there should be some interesting physics happening at the edges. So we're not the first to study the system. There's some transport measurements from Pablo Guerrero's group out. So this is just RXX in a helical trilayer graphene sample near the magic angle of about 1.8 degrees. And this is plotted as a function of filling factor and displacement field out of plane. And what you can see is that there are many intermediate features that occur at different temperature filling. So full filling tens of millivolt energy gap is at n=4 here. And there's intermediate physics that comes about because these bands are flat. Therefore, you get symmetry breaking and populate certain spin and Valley combinations. And the interesting thing is, when they park themselves, say near n=3 here, they see there's some anomalous Hall hysteresis loop here. And so there is time reversal symmetry breaking that's present in the system. You might think that this has to do with the fact that you have non-zero Chern numbers for these energy bands. So if you polarize the value sublattice, then you would expect quantum anomalous Hall states. But actually, the transport is not quantized here. You get similar physics, by the way, at fractional billets in certain cases. And so this is clear evidence for symmetry breaking, time reversal symmetry breaking. Whether or not this is tied to this picture of Chern numbers, I think is still an open question, even an open question after our experiments. But one thing that you might think or maybe hope, if you like non-trivial topology, is that the reason for the absence of quantization here is because we have all of these domain walls. So if you imagine doing some transport measurement from way over here to way over here, then you're traversing many of these domain walls, and that might affect the nature of the quantization depending on how these modes couple it. So this led us to be interested in studying, okay, what happens when you look locally? Can you really see this domain wall physics? And again, eventually with the hope of getting to looking locally at some topologically non-trivial phase. To do this, we use a single electron transistor. So this is just a metal island separated by tunnel junctions from source and drain electrodes. And if you just look at the transport across the single electron transistor, what you find are Coulomb blockade physics. They're Coulomb diamonds. And so if you just ask, as a function of the electrostatic environment of the tip, what does the current through the SET look like? You get this periodic pattern where each of these periods corresponds to adding one more charge onto the island. What we do in our measurements is we basically park ourselves, say, right here where there's some slope. And what that means is as we're changing the electrostatic environment of the single electron transistor, that causes a measurable change in current. And so in this way, it's a really sensitive probe of electrostatic potential. So we put this on the apex of the tip. We bring this tip close to our sample of interest to conduct the measurements. And it's the sample itself, which is providing the effective gating to the single electron transistor. The idea is we fix the electrochemical potential of the sample. That's the sum of the chemical potential and the electrostatic potential. As we modulate the carrier density with the backgate, we change the chemical potential. But this guy's fixed, so there's some corresponding change in electrostatic potential. That's what we're actually measuring with our tip. So in this way, we can learn about the chemical potential as we tune the carrier density in the system. This is related to the thermodynamic density of states, 1 over the thermodynamic density of states. That is, anytime there's an energy gap in the system or a low density of states, we see a step in chemical potential. This is a quantitative probe. We can actually measure what's the size of the energy gaps, or usually what we do is we do this in an AC modality for noise reasons, and then you get a peak in signal anytime there's a low density of states or an energy gap in the system. And I should say our spatial resolution is where our understanding. So, and measurement will tell you where that's. All right, so this is our measurement configuration. We park ourselves over our helical Trilayer graphene sample. We can measure it, the inverse electronic compressibility TU/Dn. And so again, you see these peaks in red here, those correspond to these large tens of millivolt energy gaps when you fully filled the flat bands near charge neutrality. There's also a peak at charge neutrality that I won't get into the details of. The bandwidth is relatively low, but if you look in between, there's not much going on. So this twist angle that we get out is about 1.5 degrees. The correlation physics, the bands are not flat enough to induce correlation physics, even though the change in chemical potential of your filament is only about 20 million electron volts. So I guess I'll maybe just skip over that detail. We can do one better. We have a scanning probe, so why just look in one spot? We can scan our tip around, and when we do that along this black line here, what we see is that the behavior that I was showing you was fairly generic. So what I've shown here in color is now inverse compressibility. Yellow means there's an energy gap. These are the gaps associated with full filling of the Moiré lattice. And you can see that the behavior is very generic. So where these occur in density, we can turn into a twist angle. So again, about 1.5 degree twist angle or so. But the point that I want to make in this slide is that actually everywhere where we look, there's only one superlattice peak. So if we had two different interlayer twist angles, then you would expect to see additional features, maybe multiple superlattice peaks. We don't see that anywhere in our sample, and this is really strong evidence that this local relaxation that I described in the theoretical model is indeed happening in the experimental system we have. So we have these uniform domains of particular stacking, and the actual angle that we're extracting here is some average of the two interlayer angles before this relaxation occurred. Is there a question?
The range you scan is bigger than the domain, right?
Yes.
So do you see features when you cross the domain?
So yes, I'll get to that. This is a saturated color scale, so you don't see it strongly, but the answer is yes, we do see it. In fact, this thing, I'll come back to in a second. This is probably a region where there's quite a bit of strain in the sample. So here you don't see it. You can maybe pick out there's something happening. This measurement actually was done before we did 2D imaging to see the domains, and so we weren't careful about what we cut through when we were doing this, but the answer is yes, you do see that physics. Is there another question? Please interrupt me. So, okay, so we can do one better. We can actually take a two-dimensional spatial map along this in this gray box here. So what we're doing is imaging, measuring in the vicinity of this nu equals 4 superlattice gap. So there's some peak in inverse compressibility. This thing is a sign of what local angle is. We can turn that into a local angle, and over a range of a couple microns by 5 microns or so, the twist angle is only changing by a few hundreds. So there's a tremendously uniform sample in terms of twist angle. But the interesting thing is we can now take a map and just ask the question, what is the maximum value of the inverse compressibility, right, at nu equals 4? And this gets at the question. You can see there's this quasi-periodic behavior that comes about. So there are this kind of triangular lattice of dark blue spots here. And if you squint, and I'll show you better data in a second, you can also see that there's a honeycomb lattice of these green or yellow spots. And the point that I'd like to make qualitatively is that within these domains, there's truly an energy gap. And so these should be most incompressible, most yellow or green. But along the domain walls, you should have one-dimensional edge states. And therefore, there's additional density states. This should make it more compressible, particularly where they meet at the AAA stacking sites. And so that's what's given rise to this kind of triangular lattice of dark blue spots. So at a qualitative level, we can map these features which we observe at nu equals 4, which happen on hundreds of nanometer length scales. So this is not associated with Moiré lattice, it's associated with Supermoiré physics, to this kind of schematic picture of different domains of uniform stacking separated by these domain walls that previously were in red, here in black. So we can look at this quantitatively, and what we find is that actually the areas of domains are larger than you would expect if you had no strain in the system. compared to, we know the angle, we can turn this into a theoretical expectation for what the size of the area is. So that's encoded in color here. So red here means that our experimental domains are larger than expected. Yeah.
So there's two angles.
There are two angles, but they locally relax. So the angle that I'm quoting is is effective. We can only tell what's happened for the system after it's relaxed, which gives one effective angle with a uniform Moiré periodicity within that Supermoiré domain. So there's no way it was this uniform. I mean, when stacking, I'm sure there's some relaxation going on, and all we know is this average after it's relaxed. Yeah.
Great. Do you see Moiré within the super?
Our resolution is 100 nanometers, so I don't, unfortunately, we can't. So one can ask the question, what is giving rise to this enhancement of the domain area? And what we find is that so first of all, I should say there was this question about interlayer twist. If there were a mismatch between twist angles, this only tends to decrease the size of the Supermoiré area. So that can explain the blue here, but not the red. And two is that so it's not a mismatch between interlayer twist angles, but if you strain one of the layers relative to the other, so you apply some heterostrain, then this actually also has a large effect on the Supermoiré area. And you can see that there's a narrow window. This is just an example case of biaxial strain applied to the middle layer, where the Supermoiré area is enhanced relative to what you would expect in the absence of strain. So I want to emphasize there are many strain configurations that one can imagine in these three graphene layers. This is just one example. We can't get quantitative magnitudes out again. We don't have the atomic resolution of an SEM to tell what the local strain actually is. And you can reproduce our data in multiple ways, even with 0.2, 0.3% strain. So even the magnitude of strain we don't know. But the fact remains it's only a narrow window of parameters that gives you enhancement of these domains. All right, so then we crashed our tip. We did some other things to the sample. I won't go into details, but this was actually lucky. We were sad at the time, but this was actually lucky because we came back with a new tip after a bunch of thermal cycles, and we went back to the same area that we had imaged previously, or very close to it, and did the same experiment. And what we found was that the twist angle, these are same line scales, same color scales every day. The twist angle is almost identical to within hundredths of a degree. But if you look at the Supermoiré domains, now they're quite a bit larger than they were before, and also quite a bit more uniform. So what happened was basically the local physics, the local structure, and also the local electronic properties weren't changed, but the Supermoiré domains were. This means that there's a decoupling of length scales in the system. That is, one can maintain the Moiré length scale, but actually change the Supermoiré physics if our interpretation is that the strain in the system changed. So this strain was not locked in during fabrication, which I think is an interesting and non-trivial statement. So I want to end, I guess I've been focusing mostly on what happens in terms of the domains of these local uniform stacking regions. But I want to end with a discussion of what happens to the domains. So normally in our measurement, what we do is we measure, as I said, with an AC technique. We apply an AC voltage to the backgate that induces an AC electric field to the sample. And the idea is if the sample screens well, then there's your parallel plate capacitor, nothing comes up to the tip. If it's incompressible, if there's a gap, it screens poorly, and then you get electric field penetrating through. Simultaneously, in order to maintain ourselves at this spot in one of the Coulomb blockade oscillations, we're also at a DC scale for every data point, applying a DC voltage to the sample to bring ourselves back to the same working point. So this DC voltage that we have to use to bring ourselves back for every data point to the same spot in this Coulomb blockade oscillation is itself a direct measure of the chemical potential. So we measure either d nu dn, we can integrate it to get mu of n, or we measure mu of n, can take a derivative to get d nu dn. And these are two independent measurements. They're done simultaneously, but they're independent from one another, and usually they agree. But there's a case where they don't agree. And I'll just tell you that this is the case that we see here. If the sample is too resistive, then what can end up happening is maybe thermodynamically in equilibrium, charge will want to come from the contacts, screen the applied electric field, and the tip will see less. But if the charge can't come to underneath the tip on a timescale of the AC voltage that we're applying to the backgate, then the sample will not be able to screen, even though it would like to thermodynamically, and you get extra signal penetrating through. So you get this kind of enhancement of the inverse compressibility, and that's what you're seeing here. This is just integrating across the gap at the superlattice peak, and you can see the AC signal is larger than the DC signal. So this is actually useful for us because in the system, as I said, there's a gap at full filling with an interesting Chern number within each of these domains, but along the domain walls, there's a drop across it. There should be edge modes along these domain walls. And so what you expect is, again, for different values, they're counter propagating. Also, there's two copies of this. This is just for one scan. This is for one domain. If you go to the other domain, red and blue arrow for which direction. So this is the theoretical picture that one would expect. We can ask the question, what do we see in experiment? And so this is just a comparison of the energy gap that we extracted in equals 4 measured with the AC modality and the DC modality. So both of these things have similar qualitative features, that is, you see the dark blue spots in both of them. But the AC one has much more contrast. And also, if you look quantitatively, the gaps that we would extract are much, much larger. So the DC measurement is what you should view as the ground truth in the system, but we can get some interesting information if we just look along a high symmetry axis. You see that there's some variation, quite a bit in the AC signal, a little bit in the DC signal, but in particular, there's a difference in how much bigger the AC measurement says the gap is than the DC measurement is. Remember, that's a measure of the effective resistance of the system. And you see that it's most enhanced in the domains in H and H bar. It's least enhanced in these AAA sites, and there's this small dip also at the domain wall. And the way that you should interpret this then is that we're measuring the local conductivity at a qualitative level. So we don't have anything quantitative here, but we can say that the enhancement is largest in the domains which are supposed to be truly gapped, and there is enhanced conductance, that is, the signal is less enhanced in these AAA sites where all of these conductive domain ones meet. So we're really making a map of the local conductivity of the system as we're doing these measurements. So I'm done. Let me just conclude that I think there's something really cool about playing around with these trilayers. There's a lot of richness, both in terms of flat bands and potential for non-trivial topology in the system. We can actually see that, in fact, there are these Supermoiré domains. So you have multiple length scales again in the problem, and you can modulate the electronic properties at all of these length scales effectively independently from one another by controlling twist and strain. You can change even the symmetries of these systems. So you can imagine getting one-dimensional lines instead of triangular domains, and maybe there's interesting Luttinger liquid physics there. And for us, we're very interested in looking at a sample that is not at 1.5 degrees below the magic angle, but at 1.8 degrees, where now you can imagine doing these imaging techniques where there's symmetry breaking you might expect quantum Hall physics. So thanks for your attention.
Okay. Questions? I'll let you choose, but sure.
It looked like you have negative compressibility over the entire conduction band. Do you understand why?
So here?
Yeah.
Yeah. Yes, yes and no. So yes, this is negative compressibility. It's not particularly strong, but it's slightly negative. That is, this is downward sloping. This is not completely crazy. My guess is this is from some long range exchange type physics that comes about. You often see negative compressibility in systems where like Wigner crystals, for example, where there's some hydrophobic exchange to take into account. So what's now understood from measurements from Elio Zeldoff with scanning split, I don't think this is out yet, but he's been talking about it, is that actually you fill one of the bands which is more dispersive first. This is the B sublattice bands, and then the A sublattice bands are flatter, and therefore there's less kinetic energy contribution to give you a positive slope, and then the exchange brings out and overall it's negative. I think that's why.
It's a so I wanted to so once you have thermal cycle,
Yep.
it become uniform. Does the twist angle changes when you thermal cycle?
So not very much. Yeah, actually, this is a point that I should have made and didn't. So these color scales are the same. The measurement is in this new black box here, so mostly overlapping. So you should compare purple, which is 1.45 degrees, to orange, which is 1.47 degrees. So by hundreds of degree, yeah, there were slight changes to the angle, but locally, the electronic properties look identical. I didn't show you a Landau fan, but it's very obvious that the local physics is exactly the same. What we think is happening is that again, there's some energetic preference. So there's an energetic competition between you want to grow domains, which gives you the energetic stacking at the cost of some elastic strain energy, which if you globally heterostrain this thing, then that costs some energy. It seems to be that what wins is the stacking energy, and so I think nature is helping us, basically, that we poked and prodded this thing, thermal cycled, and we got to a configuration that was even more favorable, which is this isotropic one.
So the size of the supermoiré is determined by the twist angle and also the strain in the middle layer.
That's right. The way you should think about that is effectively here, if you already had global heterostrain, then this green point would be very close to the gamma point between K1 and K3. And that's, if it starts out close, then that gives rise to a much larger supermoiré periodicity without having, you still get the local relaxation, but you don't have to relax as much. So it's like having one of these domains, it's already commensurate, so this is the size now of your sample in that case. Yeah.
Okay, I think that's all we have time for. Sorry to remaining questions. You can ask offline. So Nishchhal from Columbia. We'll give him an outfit. There.
People hear me? Sorry. Yeah. Okay, hi everyone. My name is Nishchhal Verma. I'm postdoc at Columbia. And today I'm going to talk about quantum geometry in correlated systems. I changed the title a bit because earlier I was going to talk about metals, but then I realized that the system that I'm talking about is more general. Okay, this work was done in collaboration with my colleagues, Harshit and Daniel, and my advisor, Raquel, and can be found in this reference. And we are working very hard to put another one, which will be so long. So before I begin, to put everybody on the same page, let's talk about what exactly do I mean by quantum geometry. So quantum geometry has everything to do with adiabatic evolution of a wave function in phase space. So if you have psi of kappa in some phase space, and if you want to describe how the wave function is changing, both the amplitude and the phase of the wave function, you can define the quantum geometric tensor, which is shown here. And if you look at the real and imaginary part, you find the quantum metric in the very curvature. The quantum metric tells you how quickly the wave function is changing, and the very phase is captured by the imaginary part in the very curvature. Now, quantum metric is very useful if you want to, again, look at quantum phase transitions. So imagine you have h of kappa, whose ground state is psi of kappa, which is some h0 of kappa h1. So if you're varying kappa and if you're going through a phase transition, the quantum metric or the fidelity susceptibility diverges. And it has been used quite a lot in that part of the literature. Now, in solid state, we are interested in systems that have periodic translation symmetry. So we have a block Hamiltonian, and the block wave function, which is psi n of k, can be written as some phase times u n of k. And in this context, there's no adiabatic evolution or anything. But what we mean is that if you were to look at the self-periodic part of the block wave function, it is allowed to have non-zero overlaps as you're traversing the Weyl zone. This is different from the full block function because the full block function is an eigenstate of our emission operator, so it would be orthogonal at K and K prime. But UN of K is not orthogonal. And that is why there is a lot of quantum geometry. There's a lot of discussion about quantum geometry in multi-band systems. So let me first begin with where to look for quantum geometry. And the easiest place to start is, again, you stick yourself into the non-interaction system. And just like in the Taylor expansion, using some identity that was pointed out in 1960s, you can write the horizontal overlap of one band in terms of dipole matrix elements of between two different bands. And this, using this idea, you can write down generalized sum rules. So here, the main point I want to make is about the Sousa-Wilkinson-Martin sum rule, which is a generalized sum rule of optical conductivity, which have these dipole matrix elements, and you get back the quantum metric of the ground. Now you can generalize these sum rules, and if you were to work in time domain, if you generalize the quantum geometric tensor with time, you can write a relation between conductivity and quantum geometric tensor and get a series of sum rules. Now these sum rules have been used quite a lot recently to obtain various upper bounds on optical gap, was pointed out by Konishi and Fu, structure factor, the dielectric function. And really what these quantities are using is that the structure factor is given by the density operator, which at small q again expands to the position operator, which because of the small q expansion is tied to the matrix elements. Now there is, it's not just all theory, there have been a lot of experiments. The first two experiments were mainly in optics, in nonlinear responses, where you cannot directly measure the metric or the geometric tensor, but you can identify what observations are induced by quantum geometry. And in the last one, this Nature Physics article that appeared last year, you can look at ARTIS, where you can look at matrix elements and sort of identify the quantum geometry. Now, the other side of literature is what happens to the quantum geometric effects when you put in some correlations. I would like to classify these type of contributions in terms of vertex directions. What I mean by that is that generally you have an operator and you construct a response function. In the particular case of flat band superconductivity, you're looking at the current operator. And what you find is that there's a connection to the current operator, which is coming because of quantum geometry, but also because you're looking at a mean field, so there are interactions. And it was shown by Verma and collaborators that if you were to look at superfluid stiffness, there is a geometric contribution, which is related to the quantum metric, and it survives in the flat band limit. So flat band doesn't have, it has infinite mass, but then still the Cooper pairs, once they form, are mobile and they contribute to the superfluid stiffness. Now, the same idea can be applied to other systems. For example, you can look at exciton stiffness. Well, the only thing that changes is that the operator that you're looking at is not on the charge current operator. It's sort of a counter-equivalent operator, and you find that there are geometric contributions. But I want to say that you don't necessarily need a correlated state. You can also look at sort of revisit vertex corrections that lead to Rule weight in a metal. And what you can see is that you can have this diagram, which is a contribution which has both some interband current operator. So the blue and green are they are the band indices. Yes.
I don't want to interrupt you, but just kind of general question. So you're doing this perturbatively.
Right.
Maybe can you comment on, what you know about qualitatively which effects are, valid, even if, say, you had a very flat band where, perturbation theory is not controlled, etc.
I'll come to that. Yeah, right. That's how it is. Yeah. So just a short answer is that I'm going to look at projected interactions in the flat band. And once I have the projected interactions, then I can talk about what type of things are on the different. Yeah. I'll come back to you.
Okay.
Okay, so yeah, I just wanted to say that you don't necessarily need correlations. You can also look at these vertex corrections and you'll find that there are contributions. And this can be measured experimentally. That you have pi Graphene, for example, and the plasma velocity is related to Rule weight, and you find that there are some quantum. Now, The single particle quantum geometry is interesting, and if you're interested in questions like what does it mean, when is it large, are there ways to quantify it, and are there what experiments can measure it, I invite you to read this review article that we put together. So it has a survey of all experiments that can help us measure this quantum geometry in non-interacting design. But today, I'm going to talk about a different question. I'm going to ask is that why is it that we care so much about a single particle quantum geometry if we are going to talk about, let's say, correlated systems and really strongly correlated systems? Now, the answer to this question should not come as a surprise that quantum geometry is important because we all sort of know Landau levels. So Landau level is a flat band system. You can write the full interactions in the UV are going to be density interactions. Now, it's only when you project the interactions down to the lowest Landau level that you start seeing some subtle behaviors. In particular, you find that the projected interactions is made out of the projected density operator, and the projected density operator does not commute. And because it does not commute, so the resulting ground state has some quantum coordinates. Now, the same idea should work for any material, if in principle should work, because most of the time here, the starting point of a calculation is some non-interacting band structure, which you can get from BFT or you can get from continuum models. And we are interested in, let's say, one band of interest, fermions, the low energy physics should be close to the Fermi energy. And you want to write the best theory that reproduces kinetic energy, which is given by excess of 3 direct KCK. And then you want to introduce interactions. Now, what I want to say is that the place where quantum geometry enters is that you want to care about what are the projected interactions. So you start with interactions in the full space, and then you're projecting it to your low energy deeper space. And that is where it matters what is the wave function at different gate sites. So very heuristically, the interaction matrix elements is a two-body scattering term. It scatters k to k plus q, and it matters how close the wave function are at k and negative k plus q. Now, so this is in momentum space, but in real space, what is really happening is that we want to write interactions in sort of the best local basis in terms of local orbitals. And there is a sort of an obstruction, if you know, like if your band has a topological index, then you cannot write exponentially localized Wannian functions. And that is where all of this quantum geometry enters. And what I want to focus on today is that given, let's say, a Chern band or Chern index of one band, what would be the best local representation of a band? So let's say, imagine you have a band with Chern numbers, so the Chern number is identical, but the quantum geometry can be very different. By that, I mean that the wave functions can be changing differently. And the best local representation for Chern band, it cannot be single orbital, but let's say if you have a quantum geometric band, it can be. And then you can have all the way from 2 orbitals, 3 orbitals to continuum, which is like an expansion in terms of infinite number of orbitals. Now, to answer this question, we are again going to go back to the projected density operator. So let's say you have some multi-band system. You focus on the projected density operator, and you get these form factors, which are block overlaps. It's not directly related to the quantum geometric tensor, because that is when k and k prime are infinitesimally close. Here, k and k prime can be arbitrarily further away. And then you ask yourself, okay, there's an operator, what is the eigen decomposition of this operator? So I take this projected density operator and I want to find new set of orbitals by diagonalizing this form factor matrix. So just to set the stage, if you have a single orbital, let's say a tight binding model, square lattice, all the phase factors are sort of trivial, all the overlaps are 1. So lambda is a large matrix, all its entries are 1. The only non-zero eigenvalue is 1, and it's given by this. So you need just one orbital to span the band. But if you have multiple orbitals, the rank of this object tells you how many orbitals you need. And the point is that for topological bands, we are going to find that you're going to need more than 1. So just to drive home this point, let's consider the simplest one-dimensional example of SSH chain. We are going to do this. We are going to look at lambda. We are going to find the eigenmodes. And now the idea is that this system has strong bonds, weak bonds, and there is that is the unit cell which has A and B sublattice. And if you look at the eigenvalues, they show this. So now there are some anchor points that we can look at. So if you look at delta equals to 1, what we find is that the charge basically sits in the middle. So you need just one orbital to describe this fact. Even though the wave functions are changing, but you just need one orbital. And to construct this blue orbital, the envelope function, which I'm again finding from eigendecomposition, is telling me what overlap should I take of this band to construct this local orbital. Now, if I go to the topological side, which is for delta negative, if you just look at the eigenvalues, it doesn't tell you much. Oh, yeah, question.
What is this lambda matrix? It's a big it's indexed by k and k prime. So
Right.
how many eigenvalues does it have?
So it depends on the mesh, but right now, if k and k prime are in the Brillouin zone, so number of the sites in the Brillouin zone. But if you put on for 2 slides, I'm going to say that the number of eigenvalues are bounded by the number of orbitals. Non-zero eigenvalues.
So these are 2 non-zero and everything else.
Everything else is, yeah. All right, yeah, that depends on the pressure. Should have said that. So lambda is a large matrix, but there are only 2 non-zero eigenvalues. Now, if I go to the topological side, the eigenvalues just tell me that I cannot span the entire band, but it's the envelope function that gives me the information that there is a 0 here, which means that to construct this localized state that is shown here in orange, I have to ignore this 1 point from my calculation. Now, I don't want to make a big deal about the SSH chain because it's a simple 1D model and the topology is really tied to the choice of the unit cell, because if I would change my definition of the unit cell, the topological non-trivial integral side flipped. So that's why let's go to a Lane model. Here we have a Chern index, so the topology is robust. We again construct the matrix. Yes.
Sorry, just going back to this again.
Right.
Can you explain exactly which matrix you're diagonalizing? Because you have 2 indices of their k and k prime, but you only have 1 on your envelope function.
I see. So what I'm doing is that envelope function is the eigenvector of this matrix. So what I'm doing is lambda kk prime times sk prime is maybe I can decide to yeah. I can do this. Okay, so I think I just wanted to say that you basically find the same thing for the Helical model. If you look at the Chern 0 side, you basically can span the entire band with 1 orbital, and there are no zeros in the envelope function. Whereas if you are in the topological side, there is this 1 0, which is topologically protected, and it has consequences. And the consequences that so the orbitals that we are creating are exponentially localized by construction. But then there is a mathematical theorem that says that to completely span a Chern band, you cannot have orthogonal, complete, exponentially localized one-year functions. So we have to sacrifice something. And that something is really the completeness. Because of that 1 0, and this was pointed out in this reference by Islam, because of that 1 0, the span of the state is not the same as the span of the entire band space. So we are sacrificing completeness to get exponentially localized states. But you can use 2 of these eigenmodes. Now, if you have 2 of these eigenmodes, then you have an over-complete basis, but you have still exponentially localized and periodic. I just want to say that there are other constructions which are very similar. So there are these compact molecular orbital construction, and they all suffer through some of the same problems because of this mathematical theorem that says that we cannot have all 3 of them. So, but really I want to talk about these density eigenmodes because, okay, for a topological band, they have this orthogonality or completeness issue. But if you have a trivial band, then they can be treated as a group basis. And that brings me to the question that was asked, like how many eigenvalues does lambda have? And what we found is that if you were to construct this operator, this expectation value, which is the one particle density matrix, C dagger R alpha C beta, inside the unit cell, it turns out that this operator has the same spectrum as lambda. And because the dimension of this operator is the number of orbitals, it means that the lambda matrix is going to have a lot of, it's a rank deficient matrix. Most of its eigenvalues are going to be 0. And not only that, we also found that the envelope function is basically creating a trial state. And I think people in chemistry have thought about this, and these are called natural orbitals. So just to recap, we have the local orbitals that you think about honeycomb lattice. So let's say A and B orbitals, those are local orbitals. Then you can have bandwidth functions, so you can consider 1A orbitals. And then these are some new orbitals which are diagonalizing this object. And what I want to say is that they can be used as a trial state for a wave function for finding one. So if you have a non-Chern band, you can calculate this object and use it to gauge the Hamiltonian or wave function, and you're guaranteed to have exponentially localized functions. And it's exponentially localized because if you look at this object, the phase of mu k cancels out. So now let's go to the original question. Okay, so all of this analysis I was doing for tight binding modules, where I already have a finite set of orbitals to begin with. But now let's talk about Moiré materials, where you have continuum modules, so they are operating in k-space. So if you look at the discrete McDonald model for twisted bilayer graphene, so the model is describing Dirac fermions with periodic potential. And if you look at the band structure, it looks like this. There is a chiral canonical kappa, which tunes to the chiral limit, where it really looks like a Dirac particle. And if I look at the low energy band, let's say I focus on just one of them. And if I look at the projected density, the eigenvalues, it decays exponentially. But then that should not be a surprise. This is consistent with the heavy fermion model, which was done maybe 2-3 years ago, where they found that the topology of the twisted bilayer graphene is not everywhere in the Feldman zone. By that I mean that if you were to calculate metric or curvature or those quantities, they're not going to vary much, except at this one gamma point. And what that means is that there is a band inversion happening at the gamma point. So if you were to take that state into your low energy input space, then you can find localized spaces. So it's not surprising that you can span the band with just a finite number of orbitals. Now, what I want to talk about are, let's say, TMDs. So TMDs are similar sort of Moiré materials, where you take 2 TMDs and twist. And the effective model was presented by you and Alan McDonald. And there you can again do the same analysis. You find the band. From the band, you construct the L operator. From that, you can find this density mode, which is a local orbital. And now you can see that this local orbital can span the entire band. So by that, I mean that the most of the band can be described by this local orbital, except at this one point where the overlap goes to exactly 0, and this is topology. So because this band has a Chern number, so you cannot span it completely. But as long as you can, but you can still span maybe like 80-90% of the band. Now this is, I picked this system in particular because it was an experiment at Columbia where they found superconductivity in the system around the Van Hove point. So this is D versus N, and if you follow that line, the little black dot over there is superconducting. Now this experiment was done at 5 degrees, and if I look at the sort of the natural orbital, it's literally the same story. You can look at the two are spanning the entire band. There's a 0 at the gamma point. But the one important difference between the two is that the energy scales are. So there it's going to, let's say 60 MeV, and this is 120. Now keeping in mind that the TC for this material is 400 million, that raises the question that is quantum geometry of the entire band sort of relevant for what's happening in the film space, right? So if I were to span the entire band, and then I need two orbitals, but I'm just interested in the Fermi surface, then I should be able to get away with simple one orbital. And to understand that, let's again construct this matrix. The only difference now is that I cannot make direct comparisons with some projected density operator, because now the projection subspace is not the entire band, but it's, let's say, just the Fermi surface. And from this, let me just explain that with a simple, let's say, quantum geometric Fermi surface. You take a Dirac system in 2D, you park a chemical potential above the Dirac point, and now you look at the winding of the spinor at the Fermi surface. And what you find is that the winding goes from 1 to 0, because at some point in the Fermi surface, the spinors will be completely orthogonal, which tells you that this, if you want to span this entire subspace, you need two linearly independent sort of orbitals, which is exactly what happens in lambda. You find that at m equals to 0, when you have the Dirac case, there's a degeneracy. And what that means is that you need two orbitals to describe a Dirac Fermi surface. But the moment you gap it out, you start seeing that you no longer need like two orbitals. You can the eigenvalues will quickly approach 1, which means that you can span the Fermi surface with just with just one orbital. Now this also makes sense. I mean, just to drive home the point, it also makes sense if you lattice regularize the system and put it in a tight binding. If you look at the honeycomb lattice, close to the Dirac point, we still need two orbitals to describe the system. But what this scheme tells you is that away from the Van Hove, let's say if you below the Van Hove, then you no longer need two orbitals. The system is basically described as just one. So this is reinforcing the intuition that if you're looking at some low density materials where the wave functions are not binding, just one orbital is enough. Now, one place where we can really see the main idea and the main power of this approach is to look at Gomel lattice. If you look at the band structure, it looks identical to graphene, except for the one flat band. But now, if you look at these orbitals, they couldn't be any different. There's no particle symmetry. What you find is that there are two of these orbitals. So the way I'm doing this calculation is that for each chemical potential, I'm constructing the Fermi surface, and then I'm doing this mode decomposition to find the actual orbital. And what this tells you is that the two Van Hoves are different. So the lower Van Hove is like an M-type Van Hove, which is known in the literature. Yeah. And what this is telling you is that you basically can describe the entire Fermi surface with just one S orbital, which means that in this Van Hove, the quantum geometry or the wave functions are not going to be that important. Third question.
Sorry, can you just say again, so on the left hand, that's just your band structure.
Right.
On your right hand, what are so these are the two
Right.
eigenvalues, and some of them are P type and some of them are S type?
Yeah, so right, so left has the band structure. For every chemical potential, I have a Fermi surface. And from the Fermi surface, I can construct this matrix. And then I can find what are the orbitals, right? And there are three orbitals. One of them is singly degenerate, that's shown in black. And then there are two doubly degenerate. And then I'm using C3 eigenvalue to say that one is S-like and
And then so how from this plot, you concluded that you really only need the S ones at the Fermi surface?
Yeah, so for the lower Van Hoves, you only need the S1. And I'm going to show something in a few seconds. So, yeah. But what I wanted to say is that for P type, I really need all three. So for one of the Van Hoves, I can get a little bit this one orbital. The Kagome structure is not that important. But for the other one, the Kagome structure is really important. All three orbitals are sort of contributing. Now you can see that if you calculate something like charge susceptibility. So this is the charge susceptibility, let's say, without any wave function, right? You get a peak at n point that's coming from the nesting. If you look at the M type, you basically get the same qualitative description. The only thing is that quantitatively the peak is smaller because some of the overlaps are from one, but they're not going to zero, or it's not as drastic as what is happening for the M type, where the peak at M is completely killed by the wave functions, right? So this tells you sort of how many when is the two Van Hoffs are not really the same. So now let me last slide. Let me go back to twisted WIC2. Now I do a series of projections. So first we know that to describe the band, you only need, let's say, you cannot take just one orbital because it's topological. But if you look at the eigenvalue distribution, it has let's say 3 or 4 modes that are important. And that was pointed out by Valentin and Antimedes, that the low energy model for this is a 3-orbital model that captures a Chern number for the first 2, and it doesn't do a good job at the third one. But for the low energy physics, we can look at this model. And now if you look at this experiment, now along this line, this is the line that is tracing the Van Hoff. And the Van Hoff is when the chemical potential is about the endpoint, when the band is taking the endpoint. And if you look at the eigenvalue, we find that basically there's just one dominant mode. Even though the band is topological, it has a Chern number. But if you just look at the Fermi surface, there is no binding, which also means that if you were to calculate charge susceptibility, quantum geometry doesn't really affect. Now you can, I want to point you to this reference if you are interested in learning more about the more serious Hartree-Fock calculation that was presented here. For now, let me conclude. So the idea of quantum geometry is about these wave function overlaps. And what we essentially did is that we sort of are writing that in terms of what are the dominant modes and what are the wave functions associated with the dominant modes. And if you are interested in what's happening in Fermi C, it can be used to give you a local basis. It will be local, but then because of the zeros in the topological case, it is not complete. It also gives you for the non-topological band, it tells you these natural orbitals, which you can use to gauge rates and find Monolayer functions. And for the Fermi surface, it basically tells you when what are the active orbitals for the Fermi surface, and when is quantum geometry going to be quantitatively important, whereas when it's going to be predictive different results. So with that, yeah, thanks for your time.
That you call.
So I did have one question about these Fu and Onishi bounds.
Yeah.
My understanding was they are bounds on the gap due to like the electron gap.
Right.
But they might not, they might not bound like if I have phonons, for example.
So the assumption, if I remember correctly, I think what they are saying is that if you look at the Sousa-Wilkins matrix ensemble, which is the metric, and if you don't have any absorption below a gap, so I would call that the optical gap, and then you can construct the bomb. So yeah.
Sorry, I didn't catch the last part. So you mentioned that the reason why twisted WC2 doesn't have a topology relevant in the experiment is because.
No, so it does have topology. So maybe let me just say that more clearly. So it does have topology. So the band is a Chern index, right? But what I'm saying is that at 5 degrees, you're interested in the experiment where they found superconductivity is when the chemical potential is sparked at that point, where it's crossing the N to the Van Hoff. And what I'm saying is that it's very far away from where the band inversion is happening. The band inversion is happening at, let's say, negative 100 MeV, right? And the Fermi surface is negative, let's say, 20. Yes.
Sorry. Do your projected density operators also form the Zhurun-McDonald Plassmont algebra?
Sorry, can you say that again? Yes.
I will do my best. We are talking about projected density operators.
Right.
do they also form the Jirvin-McDonald-Plassmann algebra?
I think there are people in the audience who know the answer better than I do. But for a lattice model, for small q, some of them do follow the GMP algebra.
What means some of them?
If you have a mute because it's a Chern band, but in general, it's not the sort of quote unquote sign algebra of GMP.
Need continuous magnetic translation symmetry for a GMP algebra. That's true. So it's outline.
Depends on whether you're on lattice or in continuum.
Yeah, you can't have it on the lattice, with one exception.
That's true. Thanks. All right.
Yeah, sort of along the same lines, if you have ideal bands, can you make any special statement about the dipole orbitals?
I don't know. So the thing is that if you so even if you take lambda levels, right, and if you sort of turn this machine, you're going to get the orbitals, the angular momentum sort of eigenstates. Now, the weight of those eigenstates projected onto the decay, let's say, clock states, does decay exponentially. So it's a matter of it will still be exponentially decaying, but there's something about how exactly it decays, which tells you whether you have like ideal bands or whether we have, let's say, PBG. At least in my calculation. So yeah, I think no, the answer to your question is everything this scheme can tell you, because if I looked at the eigenvalues as a function of kappa in PBG, kappa equals to 0 as ideal bands, and I usually.
Okay, so qualitatively, beyond just the number of orbitals, what parts of the structure of the wave function is this sensitive to?
So it's really trying to capture, okay, so you have a wave function that's, let's say, changing a lot in the Feldman zone, right? And what it is saying is that, can I describe some part of the wave function to one orbital? It's a some part to a different orbital, right? So it's sort of for doing that by just looking at an automatic way. But if you go back to like the trial state construction, right? If it's smart enough, you can always come up with a good trial state without doing any of this. That's right. But this is like an automatic way of generating. So that's how it works.
Just we use organizing authority to ask one final question. So if so you made this comment that like if you're very far away from one of the band inversion is happening, that okay, of course quantum geometric effects aren't going to matter. Now, okay, I would have actually just knowing nothing about quantum geometry, but knowing something about like the topology of the bands, have been able to make that statement. So what is it about? What are you learning from the quantum geometry in the context of this WSC2 that you wouldn't have known without thinking about?
Okay, so if you just know the topology, right? So if you think about in terms of the simplest picture, right? If you have topology, the spinner, let's say, binds around some. Now, what this is telling you is that if you are at that one particular foreign surface, how much of the blocks you're binding? If you're not binding much, so that is what you will get from it. Topology just tells you that you're going to bind. If you take the entire band, you're going to bind the entire sphere. But how, in what, let's see, what speed you're binding, or how much, how fast you're binding, how slow you're binding.
Okay, thank you, everyone. Remaining questions?
Thanks a lot, right today.
Yeah, I should look at the schedule. I think maybe it's like break is.
Right.
Yeah.
Oh. In mind. Yeah, so these activations. Yes, we.
I guess you're a final person or early in the morning. Like, okay, don't worry.
You find a big outlet. It's not really. Yeah, something like that.
Don't worry.
That's it.
Okay, I'd like to introduce Vladimir from Stanford. He will be the incoming Bill Fine postdoctoral scholar at UIM. So, can take over.
All right, so first I would like to introduce myself in the statement of here on the work. Yeah. Would you agree or? Yeah, take it. Right. So first, let me tell you like a very simple model that we decide not. No problem. You're gonna the mic is on.
The switch there.
Wait, can you hear me now? Okay, great. Right. So just let me tell you about this. This model has been studied a lot. So consider electrons in 2 dimensions with a isotropic dispersion, with a quadratic isotropic dispersion interacting via Coulomb interactions, and let's assume that the bands are spin degenerate. So for this model, there is essentially only one parameter, which is this parameter Rs, which is essentially the ratio between the Coulomb interaction and the kinetic energy. Here, N is electron density, and in experiments, this is how essentially with the electron strength is tuned. Okay, so this model, it's well understood in the small and the large RS limit. For small RS, what we want to do is we want to minimize the kinetic energy, and the way we do that is by equally populating each of the spin band, each of the spins. And for large RS, what we want to do is we want to minimize the Coulomb energy, and this is done by forming a Wigner list. Okay, in the intermediate RS regime, it's not really clear what's going on. So it's sort of a hard problem. The first thing that you may try to do is to do Hartree Fock, and when you do Hartree Fock, what you find is that at some point you find ferromagnetic fluid, meaning that you only occupy one of the spin bands. However, doing a more doing a more careful calculation, in particular for these systems, what is believed is that quantum Monte Carlo calculations they get you very close to the correct answer. And what they find is that, so here, let's just focus on the red and green lines. So the red line corresponds to the energy of the paramagnetic fluid, or just equally occupy each spin band, and the ferromagnetic fluid is you only occupy one. So what they find is that even for these large values of RS, RS up to order 40, you see that magnetic fluid has always lower energy compared to a ferromagnet. So yeah, and in addition to that, if at some point they cross, this seems to be preempted by a transition from the fluid to crystal. Here they are comparing the energies to the ferromagnetic crystal and the ferromagnetic crystal because these are the crystals that it's easy for them to simulate. But in any case, for this model, you don't expect a ferromagnetic fluid. Okay. However, in recent years, there's been a lot of experiments in materials where you have multiple valleys, but each valley is anisotropic, and in these cases, people have seen fluids that are some sort of ferromagnets. So in the first model that I got interested in was aluminum arsenides. I will talk a bit more about this, but the logic is that the way to describe this, it's very similar to the to the electron gas. We just need to add valleys and anisotropy in the dispersion. And in the experiments, what they find is that as they lower the density, meaning increasing the interactions, they see a transition from a valley degenerate fluid to a valley polarized fluid, which is some form of ferromagnetism. And more recently, I've been interested in what's going on in all these experiments in Rhombohedral Twilayer graphene. Here, I'm showing you magnetic oscillation data. So what they find is that in particular they find that in some regime of density and field, they find that the electrons only occupy half of the flavors. Okay, and just to make sure we're on the same page, when I say flavor, I mean spin and valley. In the Rhombohedral literature, people also refer to this as a spin. And another thing I want to point out is that in these two experiments, we're usually in the regime where the electron density times the area of the unit cell, it's much smaller than 1. So in reality, we can take the continuum limit and essentially just think about the long range part of the Coulomb interactions. Okay, so before I move on, I would like to give you an outline and some acknowledgements. So the first part of the talk is going to be about a toy model for aluminum arsenide. This is work done with Erzberg, Sebastian Huber, Steve Kivelson, and Agnes Valenti. And then the second part of the talk is some upcoming work with Eres and Steve. All right. So, right. So, yeah. So let's see. So first, let me tell you about the experimental setup. So aluminum arsenide. What you should know about this material is that it is a three-dimensional semiconductor. The valence, the band minima are located at 3 equivalent points in the edges of the Brillouin zone. So, but when you put the aluminum arsenide in a quantum well, there is a confining potential that depending on the width of the aluminum arsenide, the electrons tend to occupy either the X or Y valleys or the Z valleys. For this particular width, the electrons occupy either the X or Y valleys. Okay, so here I'm okay, and in particular because the band minimas are at points that are low symmetry, meaning that there is no C4 around this point, like C4 rotation around on the XY plane. The mass tensor it's generically anisotropic, and in particular for this material, Mansour Shayegan measured at some point that the ratio of the masses is around 5.2, and also the effective mass in aluminum arsenide it's around half of the bare electron mass. This is in contrast to gallium arsenide, where it's an order of magnitude smaller. Right. So this is the material, and what has been done in experiments is that they put the quantum well on a piezoelectric. So the piezoelectric is just to control add strain to that system so that they can make sure that they are so they can get rid of any residual strain, so that at large densities, meaning weak interactions, the two values are at the unit. So then what they do is, like, as they lower the electron density, they see a jump in the ratio of Rxx and Ryy, which can be thought as kinematic transition. So you're going from a phase that it's C4 symmetric to a phase that breaks the C4 down to C2. And the way they interpret these in experiments is that one is going from a Bali degenerate phase to a Bali polarized state, right? Okay, so one important thing here is that when we take this critical value of the density of electron density and convert this to a value of Rs, we find that the transition happens at Rs around 20. Okay, and this is surprising because I was telling you at the start of the talk, at least for the case where you only have a spin and the bands are isotropic, you don't really expect any transition to any type of polarized fluid. Right. So to describe the experiments in aluminum arsenide, the simplest thing that we can consider is to have the two-dimensional electron gas. So again, we have Coulomb interactions, which correspond to 1 over Q. But then the dispersions are still quadratic. But the difference now is that the mass in the x and y directions are different, and we parameterize this by parameter eta. And just to notice that when eta equal 1, that corresponds to the isotropic case, and the model is symmetric under sending eta to 1 over eta. So I will just show you results for eta bigger than 1. Okay, right. And then the other thing I want to point out is that the bands are spin degenerate. So I have 4 flavors. I have two-fold spin degeneracy and two-fold Bali degeneracy. And then the system, so if you just look at one Bali, it breaks C4 rotation, but the system overall has a C4 rotation that acts on the space combined with swapping the Balis. Okay, so the first thing that you want to do is to do Hartree-Fock, and because we wanted to understand experiments, and experiments they've only seen fluid phases, we decided to just to look for variational states describing fluids, which is similar to what Dan referred yesterday as liquid to liquid or fluid to fluid transitions. So for this model, there is not much freedom that we have if we want to preserve all those transition symmetries. Essentially, the only parameter that we have is the densities that we put on each flavor and the shape of the Fermi surface. And for simplicity, we assume that the Fermi surfaces are always ellipses. So in particular, the parameter that we had was to this renormalized mass entropy that corresponds to how elliptical the Fermi surface is. Doing that, this is the phase diagram that we found. Here we found 4 different regimes. I labeled each one by an integer f, which stands for n flavors. So what that means is that you pick n flavors and you occupy them equally, and then all the other flavors are empty. And so the first thing to notice, as usual, is that all the action is happening at arrays of order 1, which there is nothing that we can do. It's the same thing that happens for the standard 2-deck. And the other thing is that things don't seem to change that much with respect to eta. These are roughly straight lines. Right. Then there is this other issue that it's an artifact of Hartree-Fock, and I will come back to it later. But the point is that this state that it's Bali polarized is exactly degenerate at the Hartree-Fock level. with this spin polarized state. Okay, but there is no symmetry in the Hamiltonian that relates them. So this shouldn't be the case. So correlation effects somehow should get rid of this. And yeah, finally, as a comment, in general, we find that the optimal shape of the Fermi surface is always more isotropic compared to the bare one. But, okay. So, okay, the other thing is that in the experiment, there is no evidence for any 3F phase. So it seems like the transition it goes directly from 4F to 2F. So this is another thing that we expect correlation effects should get rid of. Okay, so no, right. So now, in order to take into account correlation effects, the first thing that we did, and really I mean, Agnes did, was to use versions of Monte Carlo to study the energy competition between different fluid phases. And what we found is that, okay, so essentially there are only 3 phases out of the fluid phases. So first of all, we have the symmetric phase, which is like the 4F phase, or as people also know as is the full metal. Then there is this SBP phase, which is fully polarized liquid. You only occupy one out of the 4 flavors. And then there is this valley polarized phase. So what we found is that the energy of the valley polarized state is always lower than the energy of the spin polarized state. Okay, so this is consistent with experiments, and in particular here, I'm not sure if you can see, but there's a line corresponding to the mass anisotropy eta for aluminum arsenide. And this predicts the transition from the symmetric phase to the valley polarized state is at around a raised of order 12. You know, this is just a factor of 2 off compared to what's seen in experiments, but you know, personally, there are other effects that we haven't included, such as the final width of the sample that may be important to actually pinpoint the right value of RS. But at least we got very close.
Why you're saying it's close? It was 21 or something?
It was, yeah, I mean, it's a factor of 2, right?
Oh, factor 2, okay.
Yeah, it's before was a factor of
Okay.
10.
Okay, this accuracy, yes.
Yeah. So in order to understand what was going on and see how general this is, we decided to do some analytical work. And so the simplest way to take into account correlation effects is to do the Rhombohedral approximation. So here I'm showing you the phase diagram in which we compute the correlation energy using the RPA. And we found something quite similar. I mean, of course, the values of RS are wrong again, but at least the phases that we find are the correct ones. So yeah, so we still find the symmetric phase, the CP phase, and we find that the valley polarized state has lower energy than the spin polarized state. Okay. Then another important thing here is that I want to remark on is that we need actually a finite amount of anisotropy. It's not as just with tiny anisotropy you stabilize the valley polarized state. You actually need the bands to have a significant breaking of the continuous special rotation. Okay, so as a summary, what we have done so far is that we've argued that long-range Coulomb interactions plus an anisotropy negative term is enough to stabilize a flavor polarized fluid. And the second thing is that the random phase approximation gives you qualitative results. So sorry, it qualitatively reproduces the results from variation of Monte Carlo, which is the good thing about this is that RPA is sort of cheap, and variation of Monte Carlo is usually hard. It's more expensive. And probably the more important thing that we found is that we were able to actually pinpoint that the half metal is valley polarized in this case. Right. So this is a good segue for the
Does the interaction effectively normalize mass anisotropy?
Yeah. So right. So Okay, so in this approximation, we didn't include any of that. In Hartree-Fock, yes, the anisotropy is much smaller. In the version Monte Carlo calculation, the anisotropy is also normalized, but it's normalized less than the than Hartree-Fock. So here technically what we do is you decide you start with sorry. Your trial state, it's you play with different shapes of the Fermi surface, and you see which one has the lowest energy after doing the optimization. And what you find is that the optimal eta, it's the versional eta, it's a bit smaller than the yeah. So it's you always want to be more isotropic. Yeah.
The random phase approximation is notoriously known to disregard the exchange. It was designed to resum only the Hartree interaction.
Yeah.
How on earth is it at all possible to reproduce this non-trivial isospin configuration?
Oh, I'm including the exchange, like the Fock energy.
How to include exchange in RPA via Hubbard local field corrections?
Can we let him talk? We can discuss this after his talk.
All right. So how am I doing on time?
You're doing great. You have 10 minutes left.
Okay, great. So all right. So now the second part is that I want to tell you that we have an argument to okay, so we predict that the half metals for this case is value polarized, and the half metal for dual is related by either C2 or time reversal is spin polarized. There's a caveat here that I will explain later, but the point here is that the details don't matter. Like, sorry, the details of the dispersion and the interactions don't matter that much. What matters really is the fact that the symmetries that relate the two values. Okay, so just to be concrete, let me tell you about the
What was the second part? You change the spectrum, or you change what is the shape?
Yeah, so
You're talking same object, or you're talking different object?
Different material.
yeah,
Different
yeah.
object.
So there are two different cases.
I missed.
So yeah, so the model that we have in mind is that, again, we have for different flavors, we have spin and value degeneracy. The two spin bands are fully degenerate. The interaction, just for the sake of generality, we added like form factors, but this is not really that crucial. And then, as I said before, you can think of the interactions as being Coulomb, but really you can add like gates, or you can just impose some hard cutoff at large Q. That doesn't really matter. The most important thing here is that you want the expression of the two values to be different. However, you want them to be related by the symmetry, by some symmetry. And just to so one thing here is that if the two values are if you disregard this the difference in the dispersions of the values and the form factors, this Hamiltonian is actually U4 symmetric. But when you add these anisotropies, the symmetries are broken down to U2, to two U2s. Each U2 correspond to charge and spin conservation on each flavor. And then there is a symmetry G that exchange the two flavors. And in the two different cases that I'm considering, in the case that it's similar to aluminum arsenide, the symmetry is C4. And in the case where that is relevant for this rhombohedral multilayer graphene, the symmetry is either C2 or time reversal. Okay, so precisely like the question I want to answer is which of these two half metals has lower energy? Okay, so in particular, we'll be looking at the energy of these two half metals. So what I mean by this is that I put half electrons on, say, on valley K and half vectors on valley K prime for the spin polarized half metal, and for the valley polarized half metal, I just I occupy both spin bands on one valley. Okay, so here I'm just ignoring the states that break the U1 valley symmetry, or in other words to say this, I'm just ignoring the inter-valley coherent states. And here is where I come back to this caveat about the spin polarized state. So the Hamiltonian that I wrote down, it has too much symmetry to actually be able to tell you what is the preferred spin direction. You know, in reality, I can rotate this spin, I can rotate this spin, and the energies of these states are exactly degenerate. So in reality, you should really think about this SP as a valley balance or a valley unpolarized state, but just for the sake of making the talk more straightforward, I would refer to this spin polarized state. Okay, so here is sort of the logic of what I'm going to tell you. So here B is the interaction strength. So what I want to do is that I want to compute the energy of the spin polarized state and the valley polarized state at weak coupling, and we will see that the spin polarized state always has lower energy, at least in for small b. And then, okay, so one thing here is that this is a well-defined question because you know, for small v, we know that symmetric state is the ground state because you want to minimize kinetic energy. However, because in this problem we have all this conservation of all this U1 that correspond to conservation of flavors, there is a well-defined question of asking what is the ground state in the sector, in the spin polarized sector or in the valley polarized sector. Okay, then you know so then the hope is that if we extrapolate these trends, at some point the spin polarized state will have lower energy compared to a symmetric state, and the valley polarized state would remain like higher energy. All right. So first, okay. So the first thing I want to tell you is about what would happen if you were to do Hartree Fock for the half metals. So the way I think about doing Hartree Fock is that you're trying to write down the best Slater determinant describing some state, and by best I mean the state with the lowest energy. So at least for the model that I wrote down and our models, reality the wave function that you write down is essentially a product state between the two flavors that you're occupying. So then when you evaluate the expectation energy, the expectation of the Hamiltonian, the energy is just decouple. Essentially, the Hartree Fock is the Hartree term is the one that couples the two flavors, but that won't make a difference. And the idea is that the operator that creates this Fermi C is related to the operator that creates this Fermi C by a exact symmetry of the Hamiltonian, that in this case is either C2 or time reversal. And with that, you can show that the energies are identical. Okay, so so the logic now is that seems what we're missing is that we're not taking into account any correlation between the two fluids, like the two Fermi's. So just to make sure we know that we're including everything, we're going to do like second order perturbation theory. So it turns out that the only term that makes a difference at second order perturbation theory is the process in which you create a particle Hall excitation with momentum Q in one flavor, and at the same time you create a particle Hall excitation with momentum minus Q in the other flavor. And the way to represent this is like this. So these pi are the polarization vowels of the Fermi Cs. So the idea is like for the spin polarized state, you need to take the product of the vowels for the K and K prime. And for the valley polarized, you just take K and K because these ones are valley degenerate. So I will argue in the following that regardless, we can. I would argue like this inequality holds regardless of details of what the interaction is or what pi of k is. Just the main thing is that I want pi of k to be anisotropic. Right. So the picture is that because the Fermi seas are anisotropic, there are some directions in which the fluids are more polarizable than others. And in addition, the two fluids that we're considering is the spin polarized fluid corresponds to adding two copies of the same fluid. You just occupy the k value twice, and that's the value polarized fluid. On the other hand, the spin polarized fluid corresponds to rotating one value by pi. Okay, so we can consider this somewhat more general problem where we take two copies of the Fermi sea and then rotate one with respect to the other and just ask for which value of theta the energy is minimized. So similar to before, what we find is that the energy as a function of theta can be written like this. So you have the polarization bubble of k times the polarization bubble at minus q times rotated by angle theta. So then you notice that this quantity here corresponds to an inner product between pi of k and pi of k rotated by some angle. And then you can just use Cauchy-Schwarz to show that this is lower bounded by something, and the lower bound is attained when theta is equal to pi. So in words, what this means is that you want to anti-align the directions of high polarizability of the fluid. And in particular, as I said before, theta equal to pi really corresponds to rotating corresponds to k prime. Okay, so right. So this shows that the energy of the spin polarized state is lower than the energy of the value polarized state. So let's go back to the aluminum arsenide the model and see if we can reproduce what we found. So the logic now is that if you rotate this Fermi sea by pi, you get the same. So this shows you the value polarized state is the best you can do. And then when you compare to the spin polarized case, you see that the two the high polarizable direction are orthogonal. So you lose, you're not doing as best as you can. So this shows you that at least as a common reproduction theory, this holds. Right. So again, we can introduce correlation effects. We can go beyond second order perturbation theory by doing the random piece approximation. And precisely what I mean is the following: we do a coupled constant integration where this chi naught is just the sum of the polarization bubbles of the occupied states, and we, by somewhat more involved arguments, we can show that the same trends hold, meaning in the aluminum arsenide-like case, value polarization is preferred, and in the case relevant for Rhombohedral multilayer graphene, you prefer spin polarization. Okay, before finishing, I want to make some remarks about the second case. So first of all, this effect it's dynamical in the sense that if you were to evaluate these pi's, the charge susceptibilities at zero frequencies, what you find is that they are exactly equal to each other. And if you were to do an approximation where you replace the interaction by the RPA screening interaction at zero frequency, you wouldn't see any difference between these two fluids. Okay. Another thing that we found is that the plasma energies can be somewhat misleading. So naively, because we're finding that the spin polarized state has lower energy than the value polarized state, you would expect that the plasmons in the spin polarized state have lower energy than the present in the value polarized state. However, we were able to find the dispersions perturbed in some regime, and we found that the inequalities can be either way. So, yeah. And final thing is that the degeneracy that I mentioned at the start, that the spin polarized state, it's really very degenerate because we don't have we cannot lock the relative orientation of the spins. This is going to be lifted by other effects like Hans coupling coming from the short range part of the Coulomb interaction, or spin orbit coupling. Right. So yeah. So I will just leave it here and wait for questions.
Okay, unfortunately, we don't have time for that. But so if you don't mind asking at lunch break, I think with that, we'll cut to Elio from Wisconsin. Okay, thank you for this. Welcome. Above all, I'd like to thank the organizers for putting together such a nice workshop in my geographic vicinity. Moreover, for giving me the chance to present something here. And I'd also like to acknowledge my collaborators on this work. Francesca Pauletti, who's a postdoc with George Sandurani in Würzburg, Daniele Guerci from MIT, and Ruben Seidel from Colombo. The story that I'm going to tell you is about topologically enabled superconductivity and possible applications to Rhombohedral graphene. It's really much more an abstract talk than the attempts to explain these fascinating experiments. And the word topology and superconductivity might lead to the association of topological Bogoliubov bands, and that's not what this talk is about. Instead, this talk is as illustrated by this key ring with a pretzel. It's a way that topology of fermionic bands helps to unlock off-diagonal long-range order in a situation where there is no superconductivity in the presence of trivial bands. Let me briefly recap what we saw yesterday on Rhombohedral graphene and summarize some aspects that I think are crucial, at least for the story. So you saw these pictures yesterday. It's a strong coupling superconductor. For example, if you estimate the coherence length from HC2, you find it's of the order of the interparticle distance. The normal state is spin and valley polarized. In particular, this means that the normal state is time reversal symmetry breaking, which is, of course, a crazy normal state for a superconductor. Competing states, as we see from subset aligned samples, are fractional Chern insulators or anomalous Hall crystals. And an aspect that I'd like to highlight that maybe was not discussed as much is that the superconducting phase increases linearly in this phase diagram of perpendicular magnetic field versus density. We actually saw these two pictures yesterday, the tetralayer and the pentalayer, and you see that there are these linearly increasing slopes here and here. Moreover, if you eyeball them, they seem to be consistent with about 20 Tesla per 10 to the 12 inverse square centimeters, which is actually the superconducting flux quantum, or alternatively, is the slope that you would get in a Landau band for a Chern 2 insulator. So taking this as a big inspiration, we will actually study superconductivity coming out of Chern 2 insulators. All right. Topological mechanisms for superconductivity have a long history. They go actually back to pre-BCS states in this work by Quillich, which we actually now understand is more like a charge density wave. These ideas were recycled in the wake of the Couperet discovery, works by Paul Wigman in the early 90s, and also in the context of anion superconductivity, and technically very relevant for what I'm going to tell you in the context of the transition between a bosonic fractional quantum Hall state and a superfluid. It was worked by Beckersley and McGreen. The idea behind topological mechanisms of superconductivity is that you have certain excitations or topological defects in your theory, which have transmuted quantum numbers because of topological fermionic bands. An example for this is actually skyrmion superconductivity. So here you have some water parameter which lives on a sphere, can build skyrmions, and if your the fermionic bands are topological, these skyrmions actually acquire a charge 2e, and when they proliferate, it gives you a super. Another example is actually, so this was the 2 + 1 dimensional theory. Here's a theory which is 1 + 1 dimensional, which actually I was involved in. You have Schmal and Nishchhal. And in this 1 + 1 dimensional theory for a triplet superconductor in 1 dimension, you have also skyrmions of this order commuted field. And here it's actually the spin that transmutes, and it's effectively making Cooper pairs spin a half instead of spin one. Okay, let me explain to you the idea of this topologically enabled superconductivity in 2 dimensions. As I already mentioned, this is starting from a Chern 2 insulator. Maybe I should emphasize again, it's a superconductor which comes straight out of an insulator. Chern 2 can be either composed out of 2 Chern 1 bands which are filled, or alternatively, if you have a flat Berry curvature in an inherently Chern 2 insulator, you might actually be able to extend the unit cell, double the unit cell, and thereby effectively describe it as 2 Chern 1. The local Hilbert space with these 2 colors that we have for the 2 different Chern bands, blue and red, the local Hilbert space corresponds to, you can have either W occupied or empty states. These both are color neutral, and then there is a color doublet, which we actually assume to be either energetically disfavored or alternatively in this construction of Chern 2 insulators not allowed to reach the. So actually what we're discussing is the constrained Hilbert space of a Chern 2 insulator. And to illustrate that, we use fermionic charge and a representation which is an occupation relative to the singly occupied red state. So in this case, when you have these round bracket cats, the empty state corresponds to a red hole, and the W occupied state corresponds to simply the blue particle. As a field theory to describe this, we get an effective U1 gauge theory. So these sign fields are actually the fermionic charge. They have this index alpha, which tells you that either it's a blue particle or a red hole. They couple with different signs to the physical electromagnetic field capital A, because again, blue particles are extra electrons, red particles are holes. But at the same time, they couple with the same sign to this emergent little a gauge field, which is necessary to ensure single occupancy constraint problems. This little a actually acquires its own dynamics, and that's illustrated by this Maxwell term. So ultimately, this gives a theory of 3D3 coupled to these fermions, but these fermions have topological bands. And in this case, actually, it's a Chern 1 in the blue sector, and because of this particle-hole transformation, becomes Chern -1 in the red hole sector. So this is like a quantum spin Hall effect. The only thing is that these signs actually carry charge, so we call it a quantum particle. Now, it's a brief recap. I know that there are experts in the room, but maybe not everybody is aware of all of these intricacies from field theory. I wanted to briefly recapitulate lattice QED. So of course, this is living on a lattice. We spoke about Chern bands. Clearly, there was some lattice somewhere. In this case, I'll mostly focus on the honeycomb lattice. And in order to include this little a on the lattice, we do it by a sort of tiles substitution, and you see that then little a and little a plus 2 pi are equivalent. So it's a complex variable. And as a consequence thereof, there are additional field configurations which are allowed. These are instantons and correspond, in the simplest case, to a flux which jumps from 0 to 2 pi through a given bucket. So what you see here is, as a function of time, the flux, at time equals 0, minus infinity and plus infinity. This is pure gauge, it's 0 or 2 pi. And then at intermediate times, the flux ramps up. So these are less actually real emergent gauge, electromagnetic duration. These field configurations actually correspond to a hedgehog or a monopole, as illustrated here in spacetime and hanging on its own Dirac string. And a result from the late 70s is that if you have no matter fields, but you have complex QED, these monopoles proliferate, and as a consequence, short are confined and the photon. The question is, of course, what happens when you couple this QED3, compact QED3 to this topological matter fields. They are also gapped, so you would maybe think that the situation does not change, but that's not the case. In fact, if you want to thread a flux through your sample, you have to drill a hole. And in our case, we have this what I call quantum charge Hall effect. So we have edge states running around this hole. And as you ramp up this flux here, there will be actually a spectral flow or different, except when you do this abruptly or relatively abruptly and in a small hole, you actually get a zero mode pinned in space-time at the position of the monopole. So you have a fermionic zero mode, and as a consequence, when you put the monopole into your fermionic partition sum, you get the functional determinant. There is one zero mode, so the fugacity of this monopole exactly vanishes, which precludes or prevents the proliferation of these topological states. Instead, actually, if you put a monopole and an antimonopole into the partition sum, these zero modes will hybridize exponential. There will be this exponential contribution, which, if you read this as e to the minus the free energy, it corresponds to linear confinement of these. And the photon remained massless. So, in particular, in the situation when there is no external electromagnetic field, capital A, then when there is no external electromagnetic field A, we have actually a low-lying gluon mode. So definitely that already led to some influence to the interactive. Another thing that you observe is a monopole actually has charge gluons. So how do we see this? A monopole corresponds to a change of the flux from 0 to 2 pi by 1 unit. And by Schrader formula, this corresponds to adding one extra blue particle or removing an extra red hole. So a hole, of course, is opposite charge, physical charge than the particle. And as a consequence, this means that you have inserted an overall charge of 2e into your system once you have threaded the flux from 0 to 2 pi. So monopoles actually have charge 2e. And then what you want to maybe calculate is the monopole, anti-monopole correlation. And as I'm arguing now, it actually has one more. So if you do the monopole correlator, the leading contribution that you get is exactly the one that we already had here. I mentioned that the zero modes from the fermionic partition sum are hybridizing, leading to this exponential decay. But then, if you put this, you want to put these test monopoles and anti-monopoles into your partition sum, you also have to integrate over all topological sectors of the field theory, including of those which includes other monopoles. So as a next contribution, you get a contribution where there are, spontaneous monopoles in your partition sum that are in blue here, and you have to integrate over their positions. And in particular, when they're in space-time within a radius of psi of these probe monopoles, this gives you a finite contribution to this correlation function. So the correlation function actually decays originally exponentially and then saturates because of this contribution here. And these are objects which have charge 2e. So this corresponds to off-cycle long-range order and actually. So the IR theory of actually projecting this Chern 2 insulator to W and empty is actually super good. And this can be seen more directly. If you just integrate out the fermions here, you get a mixed Chern term, and then you use just the dualities to see that this theory is equivalent to the theory of superconductor, part 3 here, and the stiffness corresponds to the gate curve. The upshot is that if you anti-Gutzwiller project a Chern 2 insulator, you get a superconductor, and if you do it with a trivial insulator, then you remain a trivial insulator. Yes.
I just want to make sure I understand. So you've got the Chern 2 band, and it's a total filling 1. Okay, so now you've partitionized it. But of course you don't know whether these C=1 bands are, they're not individually filled. They sort of have a collective filling. So I didn't quite understand how the Chern number of the band is coming into these calculations.
So
like where is it in the band structure of the particle?
So both of them are filled.
They're both okay.
Yeah. And then and now when I write it with this partial particle hole transformation, they're both filled, but they have opposite Chern number.
Right.
I integrate them out. These guys couple with opposite sign.
Yes.
You integrate them out, you get the mixed.
Okay, so they're both fully filled.
Both
so there's
fully filled.
okay. Sorry.
Okay. So the upshot is that Chern 2 is if you anti-Gutzwiller project as a superconductor, we can check this directly. To this end, we look at the Haldane model with an exodegeneracy, which we'll call color again. Nearest neighbor hopping W1, next nearest neighbor hopping the Haldane hopping W2. And when you anti-Kutsula project it, what you get here on the top is the delta dega delta, so the optimal long range water. You see that you don't even see anything that's decaying somewhere. So we have sort of the probe here, and it should be slightly decaying here, but I think you can't really see this. In contrast, if you were to look at the competing channel, which is actually charge density wave, the density correlations, these decay very rapidly. And reversely, if you went into a topologically trivial regime, and to do that, we add a staggered chemical potential, which opens the trivial gap, and then you anti-Kutsula projected. The superconductor is gone. This one is exponentially decaying, and this one has gone. Well, this is not spontaneous symmetry breaking because we are sort of by hand impose this.
Elio, that's a little bit too fast to me. You still need some glue for superconductivity.
Well, at this point, I will give you some glue in a second. I mean, I will.
So what's going on?
So what's happening here is it's just anti-Kutsula projected to doubly and empty.
But can you translate it to English?
Yeah, you can to English.
Yes.
You can take attractive, you hover.
Attractive.
Yes.
At the end of the day, it's attraction model, right? You put attraction by hand.
Yeah, I put attraction by hand. So this is not a way to explain where the glue comes from.
Do you have a political value for this attraction?
Yes.
Okay.
You'll see it in a second. Yeah.
Okay.
But this is just to see that the statement about the project. Okay. Attractive. So this is what you wanted, Alex. Attractive view Haldane-Hubbard model. I'm not explaining where the attractive view comes from, but I'm arguing that only because of the band topology this section comes to. Yeah. So accelerated nearest neighbor hopping W1, next nearest neighbor hopping W2, on-site stagger potential W0, with W2 larger than W0, you have that. And then attractive view. You can start off with doing the simplest mean field. And there are two different limits where you can do a mean field. One of them is large U, one of them is small u. You see here that locally you have separation u between the doublet and the two color singlets. And then depending on which side you're on, you have either this one lower than that one or the opposite. When you do a super exchange calculation at large u, you get just an effective spin model for this degree of freedom. It has, of course, a regular Heisenberg exchange term. But then the W0 corresponds to a staggered Zeeman field. It wants to have, depending on the chemical potential locally, it wants to have that one lower than this one. And then in turn, the Haldane hopping leads to a next nearest neighbor interaction, which is in plane paramagnetic. So it prefers actually a nail state, which is in plane, and that U1 water corresponds to the superfluid or to the superconductor. In contrast, and that I like to highlight, if you did at small u for this problem, if you try to find a sort of on the BCS or Humphrey-Fock level a superconductor, you will not find it as long as W0 is not exactly 0. And the reason is that actually the mean field equation, so there are the order parameters that are around are real dimensioning part of delta, and rho, which is the order parameter for the charge density wave. And they have the same sort of susceptibility that enters these mean field equations. It's really the exact same function. And then if you want to make this delta here non-zero, you see that you will never satisfy the set. So it will always be a charge set. You cannot find a superconductor within the subset of Gaussian states with this model. Good question.
Very nice question. Why particle and particle hole susceptibilities are the same?
Okay, so if you go to extreme limit, it has SU2 symmetry, right? It's a bipartite lattice, it's half filling. And then this actually in this case keeps going even if you like add this extra carbon mod. So there. Okay, there is a controversy. We don't know how to connect the small u and the large u, and in order to do this, now I'm leaving sort of the control calculations, but I have topological arguments which I believe are consistent even beyond the control calculation. And I use a slave rotor theory to describe this at intermediate u. So slave rotors, what do we do? So we're splitting these fermions into a rotor, and then you see here there's this particle hole transformation, the slave rotor and the fermionic charge on. So this is essentially similar to what I showed you before. You have in the first entry here a slave rotor angular momentum, and the second entry is whether you have a blue particle, a red hole, both of them or nothing. And you see that in the total occupation on each side is of course 1. That's a manifestation of the emergent U1 gauge symmetry and supports the constraint that we have to fulfill. This buys you that what used to be an interaction term is now a bilinear for the slave rotor, but of course what it costs you is that what used to be a hopping term now looks like an interaction term. Fermions. We treat this on a self-consistent mean field level. In particular, there is a part which is highlighted in green here, which corresponds to just the slave rotor part, and is essentially just a Josephson junction array on a honeycomb lattice. It has a phase transition. For small u, the rotor is condensed. That corresponds to C and psi being essentially the same. It's the X phase. And at large u, the rotor is uncondensed. It is actually mod insulating. And in this case, it means that sort of these guys here are way too far up. If I wanted to create a fermion, physical fermion, I have to pay this price and essentially qualify way close to zero. So on the left, you have a regular topological insulator. At large u, on the mean field level, you get a topological anti-mod insulator. This is how the slave rotor gets comes in, and then the quasi-particle wave goes down. On the mean field level, if you had a system which is in some region weakly interacting, in some region strongly interacting, it would imply that you here have a weird topological mod or anti-mod insulator. Here you have edge states which carry both color and charge, but then only the charge mode can enter the topological anti-mod. The color mode would be here. You had a very weird non-local color charge separation. This is not a statement which is correct for, as we see in a second, for the ground state, but actually we believe that this is a picture which is valid for intermediate temperature region. Okay, more about this mean field phase diagram. Essentially, you can have, it's a 2x2 matrix that we can think about. Are the fermions topological? Yes, no. They are topological when this angle here, which is mostly W2, is large, and they're non-topological down here. And the second question is the slave boson, slave rotor condensed or not? Is it condensed here? Then it's the same as, essentially a weakly coupled system. And then at large you have sort of this mod version. This is mean field. What happens beyond mean field? And the simplest way to go beyond mean field is to do just RPA. That's of course, there are in principle higher loop corrections, but given that most of the space diagram is gapped, we can expect that these higher loop corrections are not very important. On the RPA level, the inverse photon propagator is just the boson bubble plus the fermion bubbles. And in particular, what you get then for the gauge coupling is that it is the inverse of the sum of the inverse of the masses of the fermions and the bosons. So it's essentially the gauge coupling is given by the lower mass fermions and bosons. And moreover, I mentioned before that the stiffness and the gauge coupling are the same. Okay, so this is a way to find the stiffness, and this is a way to plot the stiffness. Same phase diagram, actually a little bit more numerically accurate. What used to be the Chern insulator remains the Chern insulator. What used to be this topological anti-mod insulator becomes actually the superconductor with the stiffness here in color coding. And then these two phases are now actually equivalent because this one is the topological trivial situation. Here monopoles separate, here T's condensed, this is the crossover. All right, what are the properties of such a weird 2D superconductor? So first of all, you see here in the inset two line cuts of the stiffness starting at the critical U. This line cut here is at 90 degrees. This line cut here is at 72 degrees, which is somewhere here. So you see that it's going away again. And then what you see in dashed is the gap, the color gap. That is essentially just the slave rotor gap. You see that this gives, at most of the phase diagram, it is a much higher energy scale than this one. So that is an idea that this is essentially a strong coupling superconductor. There's the separation of scales, and let me remind you that you cannot find this superconductor if you just search within Gaussian states. It's also giving you an idea that this is a strong coupling superconductor. It's a color singlet. It is essentially on site, right? So that means it's a trivial representation of the spatial symmetries of the problem. In this gauge theory language, vortices are the local emergent gauge charges. If you're sitting close to this transition, the cheapest excitation you can have is a bosonic excitation. If you're sitting close to this, or in most of the phase diagram actually, the cheaper excitation is creating a fermionic excitation. Fermions have valid degree of freedom, and moreover, they have this color degree of freedom that gives an internal degree of freedom for the vortex. The vortex size is given by the smallest of the coherence length of bosons of fermions. Of course, it's strongly type 2 with essentially any 2D superconductor. You can read off the Pearl length from the stiffness, essentially for free, and I just told you about the science. Pearl length is much more. And let me highlight again, the normal state for this system is actually an insulator. So it's not really clear how to compare psi and density in this situation here. And also it's not so clear where to put the transition temperature, where you would think that maybe the VPT transition temperature is roughly compared to K here, where to put this transition temperature on Judy. Because again, you just start from here, you crank up Q and you go straight for some. Now doping. What is the effect of doping? So I mentioned before that we have blue particles and red holes. So the simplest way to sort of think that we would dope the system is to spontaneously create a Fermi surface in the blue holes and here's a hole, in the blue particles, and here a whole Fermi surface in the red holes. That's of course a valid solution, but it's actually not the energetically most favorable one. And here we're borrowing knowledge from the theory of the Dirac spin liquid with the Zeeman field. The system actually wants to spontaneously form Landau levels. It is cheaper to spontaneously form Landau levels. And what you see here now is that because of the different Chern numbers, the 0th Landau level in the blue sector is below and in the red sector is above. And then if you take the difference of n blue minus n red hole, all of these guys cancel up, but this one does not cancel up. So this one being fully occupied with a magnetic field which is given by density will give you all of the density that you want to put into the system. And what you see here is that actually for two different ratios of the masses in red and blue and in different values, you see that the Fermi surface energy, so the energy, mean field energy that you get for this state is actually above the energy that you get for this spontaneous Landau level state. Okay. So the system, instead for doping, it spontaneously creates this emergent gauge field. That implies in particular that the optical gap for these fermions is increased by the density. And the optical gap is the thing that determines the stiffness. Remember that the stiffness was given by the smallest of all gaps. And here we're in the regime where it's sort of fermion dominated, but this gap is increasing in the presence of stiffness and in the presence of density. And no wonder the stiffness is going to increase as a function. All right, next, let's apply also an external magnetic field, and I add a little bit of disorder to broaden up these Landau levels, just a tiny little bit. What do we get then? Now we have different magnetic fields in the blue sector and in the red sector. Because these were electrons, these guys are mole-like, this is plus B, this is minus B. They still have the same emergent field little here. You cannot find a solution for a superfluid if you assume a homogeneous B in here. But what you actually can find here is the following solution. You can partially fill the Lifshitz tails of this Landau levels here. Partially filling the Lifshitz tails is actually going into localized, strongly localized states. And these strongly localized states are strongly localized charges, which can be interpreted simply as pinned vortices. So what you get some pinned vortices when you apply a little bit of magnetic field. That's not so crazy. But then you can also check actually, okay, so for this situation here, what's the cheapest configuration? Turns out that in this picture here, I took positive density and negative magnetic field. Then you will partially fill this guy here only. This is unaffected. And in order to fulfill the constraint, you find out very quickly that actually the magnetic field increases with modulus of magnetic field. So this is the emergent magnetic field that you need in order to fulfill sort of the overall gauge constraint. This little B field increases with B. And the little B field, assuming that these localized charges don't contribute to the stiffness, this little B field is the thing that determines the cyclotron frequency here that increases the optical gap, and thereby actually the stiffness increases with both density and. If you now assume that we have a little bit of disorder, so maybe you need to overcome a critical threshold stiffness in order to sustain superconductivity at all, you get such a phase diagram here. So what's simply plotted is this function here minus some critical stiffness. And it's in this phase diagram magnetic field versus density. And you see that there is this zero along this line here, which actually is just H over 2E. And you see that the, of course, superconducting region increases with both magnetic field and density. So this concludes my talk. This was an example where a topological band structure of fermions unlocks the off-diagonal long-range order for a system which already has sort of some attractions. In order to see that, apart from doing this numerics here, we use the slave rotor plus RPA theory to determine the parameters of the effective theory and also to sort of list the properties of such a weird superconductor. And then finally, I discussed the universal phase boundaries with the field resistance. Thanks so much for your attention.
Nice question. Suppose somebody wants to do experiment and knows that the system is a superconductor. What experiment should be done to distinguish conventional superconductor from what you predict?
So, well, I mean, of course, I tried to highlight a list of things. That's of course something that can affect. What are the experimental knobs that are in this position?
No, the question is this. You're talking about mechanism and
Yeah, I mean,
point is well taken that you have superconductivity only because of topology.
Right.
But now we go into superconducting state.
Right.
The
No, but
system
of course,
reconstructs, etc. The question is, does the system retains memory about the mechanism?
Well, I mean, one thing is this line that I mentioned. This has weird slope and increases magnetic field. Then also my question to you is, can I change the interactions? I mean, can I go out of the superconductor again and see that's a Chern 2 insulator? That's of course a very clear signature.
No, the question was about feedback from pairing mechanism on the superconducting state itself.
Yeah. Yeah. I don't know what else I can say about this.
What property is actually giving you the universal constraint on the phase boundary? Like what specific feature is
So
fixing that?
and it comes out of the speculation, and I think that there is a 2 which is essentially missing. I mean, it's divided by 2.
Right, but
I think comes from Chern.
Are they like a
original Chern 2.
like universal kinematic reason from like symmetry or like normally or something?
Yes, if you wish. I mean, I think it comes from Chern 2, so that
Okay.
has impact on our things. That's how I understand it.
So this formula, I mean, there's a squiggle there, so this is.
This squiggle, yeah. So the squiggle first of all means that their number is removed, and moreover, this is a statement which is valid in the regime when capital B is smaller.
Yeah, thanks, Elio. Very interesting. So 2 maybe small questions. So when you mentioned the statement about doing anti-Goodwiller projection on the Chern 2 band, I seem to recall that would give quasi long range order. Am I misremembering, or would you saying that's quasi long range order seeds long range order, or maybe it's a different statement? I haven't. Are you're saying it would literally give long range order? Is that the
Yeah,
statement?
that's what I'm saying, and I'm not sure why do you say this, or why did you?
Or I seem to recall for like the usual translator has this kind of non-local order parameter where like a charge with like a phase field. Like Shinsei Ryu has this kind of paper from a few years ago. And then what I seem to remember is by doing this anti-Goodwiller projection, you get rid of the non-local part and just keep the 2-point function. But that 2-point function just had quasi long range.
Sorry, so what did you say?
Yeah, sorry, maybe it's a bit that may be better to discuss. Yeah.
The paper, maybe it's not how.
Sure, but I might be misunderstanding the statement there. And the second question, so you nicely emphasized that you need the topology to get the superconductor. So just to kind of make sure I understand, you're saying if you were to repeat everything with trivial bands, but a strong U limit, you would get a bosonic mod insulator or something?
In this case, you stay in the, I mean, in the simple toy model, it remains a charge density wave just throughout. But it's a charge density wave that is sort of externally applied, right? You have a staggered potential. In this case, we created logically triple bands from the then you would end up in a state which is like 2, 0, 2, 0, 2.
I see. Yeah, thank you.
We have time for maybe one more.
This is a naive question, but maybe I missed it. So can you go over again? So basically the role of the Chern number in your, effective parton theory, among other things, is to prevent the, internal gauge field from being in a confining phase.
That's right.
And that is essentially the thing that puts it in a superconducting state and not a mod state.
That's essentially correct. Yes.
So can you say again why that is? Just
Okay, there are different ways of seeing it. I mean, either you integrate the fermions, you get a mixed Chern-Simons term. That's the group.
I understand the argument about confinement. My question is, how do you get from saying, if you're not in the so if you're in the confining phase, okay, you get this mod insulator. Why is it that not being in the confining phase puts you in a superconducting state?
The summary slide is slide. There are two ways of seeing this. So the upper part is you simply calculate the monopole correlator, and the monopoles carry charge too. And you see that this thing is off the envelope before. And it gets that the monopoles really are, well, the monopoles by themselves, right, are linearly confined, but then you do this calculation to the next order, and then you get that there is a sort of this asymptote that you reach. And the other thing is alternative calculation, and of course these things are known, that's simply used here. You get this mixed transaminase term, and then this equality.
Great, let's thank the speaker. Yeah, I'm gonna be very lazy and stay seated. We have Jed from Rutgers.
Well, this clicker works for the pointer line to a global record.
I also have another remote and Dom call. Usually leave it enough.
All right, hello, can everybody hear me? Yeah, great. Thank you, everyone, for being here, and fantastic workshop. We've been learning a lot. It's very stimulating, a lot of different topics. I'm happy to contribute to maybe changing the pace of the discussion. So I'm going to shift up gears quite a bit and talk about something we've been working on at Rutgers over the past, I'd say, 5 years. Let me start by thanking my collaborators. So really, this has been driven by my colleague Jack Chakalian's experimental group, using laser pulse deposition to make high-quality thin films of pyrochlor iridates. And pyrochlor iridates, about 10 years ago, were being advanced as a very high-exciting tunable system, but the materials weren't there. And I'm excited to tell you today, I think they're basically getting there. And so it's a really interesting direction to take. So I'll be talking about two pieces of work, but mainly getting to this most exciting and interfacing these different materials. So I want to step back a bit. I'm going to stepping back. I'm going to ask kind of what is driving these interesting novel quantum phases we're seeing across all these different systems, and then try to put things together to make new things. Okay, that's going to bring us into these iridates or these pyrochlors, and I'm going to convince you that europium iridate is a pyrochlor, is a Weyl semimetal, which was the big beta for quite a long time. And then I'm going to discuss and review classical spin ice. We'll then put them together into a heterostructure and use the surface states of the Weyl semimetal to probe the properties of spin ice, which is an insulator. Okay, and so it's pretty interesting, and I think there's a lot of room for other people to get interested in these problems. So I hope everybody finds this talk interesting, and maybe outside the beaten path of what we've seen this conference so far. So stepping back, what I want to ask is, what are routes to novel quantum phases? So we saw one dimension rigorously taught us right away that fractionalization can happen. And now we have our tunable 2D systems. It's more and more amazing discoveries coming every year. We also have been searching for a long time for quantum spin liquids, and due to frustrated interactions. So we're quite comfortable using frustrated interactions to get large quantum fluctuations and drive novel phases. And we also now have topology very much at our control. We've had it for, of course, a long time under magnetic fields, but now we have topological insulators, semimetals, so on and so forth. So this talk is asking the question about the interface. If I bring 2D materials, two different materials together, the 2D interface can introduce an entirely new system that's worth thinking about. So maybe we can find novel phases and interfaces between totally different materials that can actually be grown in experiment to find other ways to get 2D systems that you never would have imagined nature to produce on its own. Okay. So that brings me to pyrochlors, and I was drawing pyrochlors here for a reason, because the pyrochlors are going to be being able to do this using lattice matching. So pyrocores, if you're not familiar with this, it's been a while maybe since this topic's been discussed regularly, maybe since I was a graduate student. But basically, this is quite exciting 2014 area. You can see all these review papers. So basically, you have rare earth and transition metals, and they form corner-sharing tetrahedra. And so all of this talk is going to be looking along the 1-1-1. That's how all these experiments or actually materials are grown. The 1-1-1 is really interesting because you have layers of Kagome lattices and triangular lattices. So all these 2D systems we're thinking about, we have layers of them right here. And conventional magnetic phases that we see on these pyrocores are going to be called the so-called 2 in, 2 out. This is the ice rule. And all in, all out, that's what we're going to see today. And the monopole phase would be 3 in, 1 out. Okay. And so we get into some more detail. And so let's think about actually now including interactions and frustration. We're going to think about the iridates here. And so we're going to throw the microscopics for a second, the iridates. So if I take the iridates and I think about the microscopics, I go down to a crystal electric field splitting that opens up a gap between EG and T2G. Then I add the spinoric coupling, which since I have 5 electrons, I fill my 3/2 state, leaving me with a J half left over. And that charge is distributed in a non-trivial way such that I have spins at the corners, basically corners of the tetrahedra. Okay, so this kind of emerges out of this. And then theorists started drawing very nice pictures. We're thinking about varying interactions. And for a coupling, you can get a wealth of quantum phases. But our experimental colleagues are grounding us with reality here. So here's basically why you can do this, is because the tunability of these basically magnetic transitions are readily tunable by the size of this ionic radius. If you want to try matching systems with very close ionic radii, this would be a very good system to try to mix and match these materials together. Okay, and this is not necessarily an insulator. It's a bit more subtle than that. And this europium case is going to be something I'm going to focus on here in a second. So this Weyl semimetal in the iridates, it's actually probably, I think, the first prediction of Weyl semimetals, but yet been argued and debated since that. And so I think this paper in 2021 is quite definitive. I mean, at least for time reversal breaking, inversion breaking, you can very definitively demonstrate it. For these iridates, though, it's been very, very challenging, which is all time. Okay, so Weyl semimetals in the pyrocores. So let me just remind you very briefly. So Weyl semimetals are going to have some basically pair of Weyl points. If I break time reversal, I can get away with just 1 pair. If I break conversion, I have to have 2 pairs. These are sources and sinks of Berry curvature, and these are linearly touching points in 3 dimensions. So inversion symmetry, breaking materials, we've made amazing progress. This is antimatter arsenide, and the reason why we've made amazing progress is because you can match ARPES and ab initio. So you can get very good agreement between theory and experiment, and you can check, aha, I found a Weyl semimetal. If you come to the iridates, it just becomes a much harder problem. So if you look at this is the first real prediction that for Weyl, 2011, in these iridates, okay? But now these are strongly correlated, and the symmetry, unfortunately, is a problem, okay? Let me remind you of this. So the correlations, basically, you cannot get good resolution ARPES, and your ab initio is untrustworthy. So either way, you don't have a good estimate. My colleagues at Rutgers did single site DMFT plus DFT. They found no Weyl phase. They found a trivial insulator. And Andy's group, Andy Millis, did cluster DMFT and found a small semi-metal Weyl phase, but nobody knew what the value of the iridium interaction is. So there's a big question. You can't answer this theoretically, really. So we're going to answer this using experiment. Okay. And the other issue is symmetry. So for times of broken Weyl, you have this really beautiful result of Anton Burkhoff that the anomalous Hall effect is dictated by the distance between Weyl points. Okay. But now you go to the iridates, and when you apply this to the iridates, you get basically so many Weyl points with equal and opposite so-called Chern vectors. They sum up and add to 0. Okay. So a perfect pyrocolor iridate gives you 0 anomalous Hall. Okay. So it's a very hard problem. But Nagaosa had this beautiful idea that, if I could grow basically thin films in the 1-1-1, I break that symmetry strongly, I should get a sizable anomalous Hall. Okay. People tried to do this for a long time, but the thin films just weren't high enough quality. And this then became, Jack Chikalian's big effort at Rutgers, and he basically was able to achieve this. Let me show you some TM image. So this is europium iridate, and he grows this on a very trivial, boring insulating substrate, non-magnetic. And you can see a very nice, high-quality interface there. Here's my europium iridate thin film. They can do X-ray resonant magnetic scattering to confirm this all-in, all-out magnetic order. right at that critical temperature is exactly where you see this anomaly in the resistance, which picks up some semi-metallic, maybe power law-like insulator at low temperatures. Okay. Another reason why to take the europium example, these other iridates have more insulating-like low temperature behavior. So the europium example is a good candidate for Weyl of these strongly correlated samples. But look at this anomalous Hall signal that's stable at low temperature. This is I'd say, a beautiful experimental result that resulted in coming from a 60-layer sample. When they made the samples bigger, the signal went down significantly. When they made it thinner, it went up. Okay. So then we got involved doing theory for this. So we basically said, well, I can just now fit the experiment to tell me what I should take, right? Because I now have the experiment. So we can do is a LDA plus U, and then find where I need to sit. So I can basically do an anomalous Hall conductance map. And I can find that, for a pretty good estimate of the Fermi energy and this anomalous Hall signal, I can reproduce for a U on the order of 1.15 to 1.3. Okay. So I'm going to basically take this as a fitting of the experiment. So this is a reasonably good model. And we could actually scale this up significantly using this method called coronal polynomial method. We could actually scale our calculation up to 61 layers, which is the size of the experiment, showing very nice 1 over thickness of the conductivity. Okay, so this was it's the first strong demonstration for thin films, and we have one more piece of evidence. I mean, just from terms of the thin film, which would be the surface states. So, but this didn't come in those samples; they still being improved, and so this is the most recent data I'm about to show you. But this is theory. So you have a prediction of this is the colors, your spectral function, and these are your Fermi arcs. It's a very complicated system. There's like 24 Weyl points for this value of U. So you have a really complicated Fermi arc structure. As I told you, the 111 growth gives me either a triangular lattice or a Kagome lattice. So these are two different terminations. You'll get two different types of surface state structures depending on that termination. But nonetheless, you can now do computations of the resistance. So this is an experiment seeing a very nice flat plateau characteristic of surface states of a topological material. And we can get that very nicely within the theory. You can go to larger layers here and see that it converges. Okay, but if you get rid of any surface states, you take a periodic boundary conditions in all directions, you get the expected power lens. Okay, so this is really confirming. Okay, I think we have planar Hall. We have other evidence we can talk about offline. It's not published, but it's really convincing to be Weyl. Okay, fantastic. So what I've shown you is I found a topological Weyl semimetal. Very good, but the whole motivation of my talk was to try to find new phases of matter, or find new ways to find them, maybe. Yeah, my talk won't find them yet, but this is maybe a way to get there. And so what I'm going to now do is I'm going to bring in spin ice. Okay, why? A, Jack can grow it, and B, it's really well understood. The classical spin ice is incredibly well understood, and there's people's whole career studying spin ice. So I'm in no way a level of that expertise of spin ice. So I'm a novice, but I'm learning. And the fact that they can grow these together is a pretty amazing feat. And you can also now grow other ones together. But let's start with spin ice, okay? So let's start. Let me just remind you about spin ice. Why has it got the name spin ice? Well, these corner sharing tetrahedra, when you have the 2-in, 2-out structure, it mimics water ice. And it actually much more than mimics, the entropy is going to match that of water ice. So you can actually argue this just going through a simple, basically, exchange argument, which is basically quantizing all along the local cubic 111 directions of the tetrahedra. When you do so, you find a so-called ice rule, which basically means that these Ising spins on these quantization axes have to sum to 0. So this ice rule gives you basically an entropy you can't release by tuning up the temperature. And so this is experiment from Art Ramirez. I think he was at Bell Labs at the time. And this is a specific heat characteristic of spin ice. This is the spin ice transition. The spin ice is a short range ordered state. And here you can see this entropy, and it goes to a plateau value, which is precisely Pauling's ice entropy. It's a pretty beautiful result. And people are really excited about this because ice melts. This doesn't. So you can watch that entropy go away without destroying the system. Okay. So here's our dysprosium titanate. And look, unfortunately, those local nearest neighbor interactions are not nearly sufficient because J is 15 over 2. And so the dipolar interactions are very strong. Okay. So if you actually want to do a calculation that looks like reality, you got to take into account the long range dipolar interactions. And luckily, Monte Carlo at other small systems like 4 cubed actually mimics this because it's a short range ordered state ice. So it's the dynamics is very slow. So but the Monte Carlo is incredibly difficult to converge. Okay, but people have whole careers in this. This is understood. Okay, so let me just show you some of the spin ice phase diagrams. So here's one. So here's out of plane field. Okay, so what you can do is you can go from spin ice into something called Kagome ice. This is a crossover, but basically all those Kagome planes kind of decouple. Okay, and then you have a first order transition into a magnetic monopole phase, 3 in, 1 out. You can also now tilt the angle, okay? And you can go through this magnetic monopole transition as well, just by tilting the angle at fixed field. You have a question? Okay. Sorry, Ben, you looked. Okay, so you basically, these are bulk, okay? And we're doing thin film, so the critical values will be quite different. And there'll be one example at the end where I can actually compare to a thin film, and we'll come back to that, okay? But basically, let's ask this question. Can we probe these phases or transitions through resistance in the EIO interface? Okay, this is the question we asked. Well, I didn't really ask it. He showed me the data. Okay, so they made this device. Okay, and it's a, I mean, rather remarkable thing to be able to make this. So we have two different types of magnetic order. This Weyl Semimetal is time reversal broken, all in, all out. This is classical spin ice, 2 in, 2 out, and you have this now interface. And what's happening at that interface? Okay, and so they can do TEM on this interface, and you can actually determine that the termination is between a Kagome plane to Kagome plane. So that's very helpful because we want to couple these layers. Okay, and then we can now imagine from the top view what those local moments of dysprosium are going to look like from the image of iridium, because those are going to be like the strong local moments on the other side. And they can also measure basically a very nice plateau in the resistance in this heterostructure. So adding this interface didn't destroy any surface states, okay? But now I can apply magnetic fields and tune the phase of spin ice. I can tune the nature of spin ice and change the response of europium iridate. So I have to convince you of that first, okay? So I first have to demonstrate that actually these surfaces interact. It's very much, you can make such a device and there could be very, very minimal coupling at that interface. So here's, I think, very strong evidence. So this is the percentage change of the magnetoresistance. And here is no europium, sorry, no dysprosium titanate. So this is just that boring, trivial insulating substrate. You see no angular dependence. The different colors are different angles. You put this on DTO, you see a very strong angular dependence. We can then draw for 2 Tesla and 5 Tesla this angular dependence. Here's EIO, nothing happens. Here's this heterostructure. And lo and behold, what are we doing? At 2 Tesla, we're going through the phase diagram without a phase transition. And 5 Tesla, we're going through a transition like this. And this appears as this peak in the magnetoresistance. Okay. So that's our hypothesis. I have to do more than that, but let's just keep going with this. So now I can do in-plane magnetic field where the effect is very dramatic. So here's now in-plane magnetic field varying the angle and increasing the magnetic field. I've stared at this for a while, so let me summarize the data for you quickly. The first is you get at large enough field, it goes to you get this 6-fold emergent anisotropy. These peaks sharpen at large field, and there's an emergent 2-fold anisotropy that I won't capture. It could be strain, it could be something emergent. That's beyond any theoretical modeling we had here. But if you look at these angular plots, it becomes very sharp and isotropic. Okay, so Jack showed me this, and we then had a bet. We had a bet that we were scanning through the phase diagram, and I could capture all of this qualitatively via electron spin scattering at the interface. Okay, and so this is now a hypothesis. So we're hypothesizing that I'm scanning through the ice phase diagram and I'm picking it up in the magnetoresistance. So now I need to model this and develop a qualitative picture for this. That's what this talk is going to do. Okay, so quantitative understanding or field theories or everything beyond anything we're doing here. This is basically scratching the surface of this problem. Okay, so let's try to model the heterostructure. So we have our europium iridate, we have dysprosium titanate, which is classical, and we have them interacting. So the europium iridate, I can build a Wannierized model, and this comes from some LDA plus U self-consistent solution that I can simulate up to big sizes. So I have this from this previous paper. Now I've mentioned to you I can do classical Monte Carlo to handle dysprosium titanate, and now I have to couple them together. So the fact that that TEM image was such high quality, I can build a pretty reasonable model for this interface, so I don't know any of these scales. So if anybody's interested in trying to compute those scales, you know, that's a very nice problem, right? But what we're doing is making an assumption basically of just tunneling, which gives you a condo coupling at the interface. This is a classical local moment coupled to itinerant electrons, so it's not the conventional condo, but this is seen in other itinerant magnets as well. So the machinery for some of this stuff exists, so we're not going to use any of it. So we now want to estimate the interfacial contribution to the resistance. So how would you do that? So what we did is a Boltzmann theory. And so what you can do within Boltzmann is compute an interlayer scattering lifetime. And this interlayer scattering lifetime is now where we can use second order perturbation theory. And this is kind of where the magic comes in. And the second order perturbation theory allows you to solve each problem independently and then convolve the solution to get the full answer at the perturbative level, okay? And what are these two terms? This is the surface spectral function of the Weyl Fermi arcs. This is the spin structure factor of spin ice. By convolving them, I think I can get a qualitative picture for what's seen in the experiment. And so what does that mean? So here's my surface spectral function for my Fermi arcs. You have to get all the effective points at KF, and then overlaps to build these couplings. And then from this, we're going to take Monte Carlo snapshots. So I'm decoupling the problems. I'm solving the two problems. I'm putting them back together a la perturbation theory. Okay, and putting them together and solving them at once is potentially possible, but that's something that is nothing we've touched. But I welcome people to take on this problem. Okay, so let's show you now. This is just the structure factor of spin ice in this in-plane magnetic field. What is known is that you get a long-range ordered Q equal to 0 phase where the spins point away from the field. You get a short-range ordered Q equal to X phase around this angle and then back to 0. The spin structure factor responds dramatically. Okay. Now I'm going to look at this basically structure factor different wave vectors, and here's basically this peak. And then what you have to do is you have to then convolve this peak with the spectral function from the Fermi arcs. Okay. So as you can see, when you convolve them, you get a weak signal, a large signal, a weak signal. Okay, so this is my qualitative picture. It's basically a phase space scattering approach to understanding the experiment. And then you can look at the outcome when you compute the actual resistance by integrating this lifetime on the Fermi surface. And here's the experiment. And indeed, we qualitatively match this very nicely. As I said, the scales are quite off. That's just because we're doing this for a thin film, and all the theory is done with periodic boundary conditions in all directions. Because the film is even harder, but this is a pretty non-trivial problem. I think we all would agree. So you need to start somewhere. Okay, but we can capture all of this other than any twofold emergent, basically symmetry breaking. So let me finish. I'm going to finish by convincing you with other data independent from us that everything matches up. So this is the 111. Okay, and this signal is just not as dramatic. So I think the peaks around 60 degrees are much sharper. And so this transition shows up at this little bump at 20 millikelvin, okay? And if you now do this calculation, what's happening is you're going to this Kagome ice crossover before you transition to the magnetic monopole. And we compute this interfacial resistance, and we get precisely this. We can now compare scales from the experiment with an actual study of a thin film of DTO on its own. And lo and behold, we get right here at HC1 is right where the transition pops over, and then the maximum of the bump is right in the middle. So you're actually detecting the magnetic phases of an insulator through the surface states of a topological Weyl semimetal. So I'd like to end basically. So I hope I've convinced you that europium iridate is a Weyl semimetal, and I've also showed you that you can couple europium iridate with dysprosium titanate to basically probe the nature of the insulator. But yet we have yet to include any back reaction at that interface if some novel emergent phase happens at that critical point or in that magnetic monopole phase. We have no idea. Right? And the other thing I can tell you is that we are growing other interfaces with, for example, quantum spin ice, and they can be grown just the same quality. And so we can tune through quantum spin ice phases where you expect there's a U1 quantum spin liquid in a regime of the phase diagram, and you can couple this to Weyl Fermi arcs. And so you can probe all sorts of other aspects of spin ice, which has been out of reach because of optical selection rules and things like that. So thank you for your attention. I hope you found this talk of interest.
You have plenty of time, so essentially unlimited questions.
Yeah, please.
Yeah, I have a question for the classical part. So I was actually doing the Monte Carlo with Peter Horse was on Sensation some time ago. So For the classical part, in order to see the Q2X state, you actually need a long range dipolar interaction, or at least secondary.
We had the long range dipolar.
Yeah.
Sorry.
But then you always have the 1-1 field, and your angular price for the tilt field component, right?
We have any field.
Yeah. But then my question is, when the tilt field component along the -1, -2 plane, when that's very small, what is the ground state?
Oh,
Yeah.
I mean, we're not
Part.
we're not answering anything about spin ice better than you have. We're just using everything that you already know. So you're asking, I mean, let me get to the picture. Sorry, hold on. Here. Here, for example.
Yeah.
So, yeah,
That's
go ahead.
the two order state when you have a very large tilt field component. And you have the 6 4 and 3 of them will be Q0, 3 of them will be Q2X.
Yes.
But my question is, when this tilt field component, in-plane component, becomes very small, then what is the true ground state for the dipological gas? Because there's some controversial about about this region. Do they see any signature of the large order state?
So what exactly are you asking? You're asking to reduce the in-plane magnetic field and put it out of plane? They only did these two scans. They did this and they did this. Yeah, is the answer here?
Okay.
Yeah, they didn't, I think you want this out of the plane. I think that's what you want. They don't have any data there. But
So I'm missing something basic. So this problem reminds me, an intention probably Elio is to, when you create two-dimensional gas from two insulators, are these guys insulators?
one is a semi-metal,
One is a semi.
so close to an insulator. It's pretty close.
So, and now
It
you
is.
have two-dimensional gas.
Huh?
The
3D.
interface now becomes conducting as two-dimensional.
Well, the surface is conducting before you couple them because it's topological.
Oh, I see.
More like making a condo.
No, it's not,
Stays-
yeah, you're making conduct.
Space conducting, and then when you say interlayer scattering, meaning scattering from what layer to what layer?
Fantastic. So I mean that, so sorry. This gives off, so the electrons are coming from this layer. This is an insulator. So the electron hops here, spin flips, hops back. Or potential scatters.
Okay.
Okay, and that's basically this process. Because it's a T-squared process.
From last layer of one phase.
It goes boom, boom, until you get like a condo coupling.
Last layer to topmost layer of reverse phase and backwards.
Backwards, it goes back to the metallic phase.
Okay, thank you.
Yeah, exactly. Yeah.
Is there anything weird about the Kondo exchange mediated by the Fermi arcs and?
Yes,
Yeah.
totally. Yeah, I mean, there's a whole shape to it, and I mean, as I said, we didn't, we just try to qualitatively explain the experiment. But yeah, there's, you could imagine, for example, integrating out fermions and thinking about the dynamics of spin ice optically. You could probably see the two timescales of the Fermi arcs and then of the spin ice. It's a very interesting non-equilibrium kind of even maybe question there that you can think about. Yeah, but it's totally wide open, I'd say. But the shape is interesting, and it's not just local. Yeah. Yes.
So maybe a related question. So, this guy on top is a Weyl semi-metal. Are there quality, and you could of course have put, I don't know, a semiconductor or a metal on top. So are there qualitative signatures in this response?
So
The topology.
So you don't get, so if you don't have like a metallic surface, you just don't really, you don't get a response.
Yeah.
So if you take a trivial, if you take like say it again, sorry.
Let's say like closed 2D Fermi surface versus.
Yeah, so in the supplement, you'll see like circular Fermi surface and you get different responses
But do you
than
understand?
Fermi arcs. No, we don't. I mean, we don't. I mean, the role of topology, other than the fact that the only role of topology here is giving me surface states to detect the magnetic interaction. I think that's, so the other way it appears is, I mean, in the negative magnetoresistance, for example, this is negative, this is a negative magnetoresistance, and this is a signal on top of it. So like the topology is in there because you're probing the transport of a Weyl semi-metal, but you have this surface contribution that's non-trivial. So I'd say all the topology of Weyl should be there. I think that would be the fair answer. But on top of that, you have a subleading contribution from the surface that if you have accurate measurements, you can detect.
You're saying open versus closed Fermi surfaces look very different.
They look qualitatively different, but I don't have like a quantitative statement to make. Yeah. But in the supplement, I mean, you can check and we can talk offline. Please, yes.
Can you tell us how big the epitaxial strain is? And is it easy to justify that the dysprosium system is still in the classical spin ice phase and that the EIO is in the semi-metric phase as that volume is?
Fantastic. Okay, so I can give you the evidence we have. So the first evidence I still am in Weyl would be my surface transport signature. Where was that? Here. So here's one evidence that it's Weyl. And the anomalous Hall response is also there. I'm not showing it, but you have this flat, and this is for both. You see no DTO with DTO, you see? And then you also have the negative meter resistance I was just talking about. That's very clearly like 1/b², and it looks very conventional from a Weyl perspective. For the spin ice, we have no probe of spin ice. We only measure resistance. It's a fantastic question, but that's why I would say there isn't, as far as I know, any spin ice measurements at a plane like this with angle. I could be wrong, but we were looking in the literature. We had bulk examples varying angle, and we had at a plane thin film to compare. And the at a plane thin film, I would say, would be the best evidence if you want to associate with existing literature spin ice would be here. So we said from a theory perspective that this should be this crossover. This should be this. That's my theory interpretation. You now compare that to a measurement of DTO thin film, and you get that matches.
And how big is the strain on YSE?
Okay, that's the first question you asked. So that is a great question. And I want to say that they tried to estimate something roughly from the TEM, but Jack never really believed that number. So I wouldn't. I think it's low. It's a small amount of strain, like less than 1% or something, because of the quality of the. I mean, they're just basing it off of the quality of the TEM.
What do you mean the residual strain, which is hard to determine? I just mean the mismatch. What is that?
They're lattice matched. They're lattice matched. They grow lattice matched. So he grows everything. Everything has the same lattice constant that's after it's grown. So it's not the ground state. They're all with one. Even though this wants to be over here, as far as I know, he grows them all with the same lattice match constant.
So they're fully epitaxial, fully strained. But what's just the bulk lattice mismatch between the two equilibrium lattices?
I think I don't know, but this is the only data I have to answer your question. But yeah, I mean, this is not going to answer it because this is the ionic radius of that atom. It's not the actual atomic spacing of the solid. So yeah, it's a good question. I should put that in here. Thank you. Yeah.
All right, can you all hear me okay? So thanks for the invitation. It was a very nice workshop. And so I'm a postdoc in Kinfei Mak and Jia Shen's group at Cornell. This is a group that's focused on basically studying electronic and optical properties of two-dimensional layered transition metal dichalcogenide semiconductors. And so the work I'm going to tell you about today is basically trying to develop a new scheme that can allow us to sort of probe electrodynamics of these materials at high frequencies, in particular at the sort of terahertz frequency rate. Okay. And so, in particular, I'm first going to sort of give some motivation for this, and then I'm going to show you how our scheme works under two sort of different regimes. Okay. And so basically what we'll be doing here is trying to use the excitons in these systems, which live at a high energy scale, right up in the sort of EV energy scale, as a sort of window into the dynamics that's taking place at terahertz frequencies, right, at a much lower energy scale, down in the few millivolt range. Okay, so first we'll take a look at how this sort of scheme works at zero magnetic field. And to sort of spoil the surprise, basically what we see is that we can image some kind of propagating plasmon modes in this regime. Okay. We'll then take a look at what happens in high magnetic field, and then what we see is that the system behaves quite differently. In fact, we'll see that the sort of electrodynamic response seems to be really dominated by Landau quantization. Okay, and so this is a talk that's sort of well on the experimental side of the spectrum, and I don't have any fancy correlated states to share with you today, only Landau levels in terms of topology, but at least at the end, I'll sort of point towards some future directions that may be of interest. Good, let me just acknowledge the people who contributed to this work. In particular, I worked very closely with Chirag, another postdoc in the group. We were also lucky last summer, we worked with Suhong, a student from HKUST who contributed a lot here. And on the theory side, toward the end of the talk, I'll show some sort of analysis and a picture that was provided by Dima, who's another theory postdoc at Cornell. And of course, it's all possible because of the high quality boron nitride from. Good. So what's the point of doing these sort of terahertz frequency measurements? Okay. I think maybe it depends on the audience. Some people are interested in making classical devices. Maybe some people are interested in making quantum devices as well. I hope for this audience, it will be sufficient to make a sort of empirical argument. Okay. We know we've seen lots of talks in the last few days where there's sort of interesting phenomena happening in interesting materials on this sort of low energy scale of a few millivolts, because this is often close to the energy scale of interactions in these systems. Okay, and so precisely if you have a photon energy of 4 millivolts, that's 1 terahertz. And so this is sort of matching well with the sort of typical energy scale in these systems. In other words, if you think that it's interesting to do measurements at a few tens of Kelvin, right, then you should also maybe think that it's interesting to look at electrodynamics on this energy scale. Okay, and I hope you'll forgive me for taking a concrete example that motivated me to do this from my previous work. I used to do scanning SET measurements that Ben explained nicely. This is some twisted bilayer graphene we looked at. Its density versus magnetic field. I'm not going to explain anything about it. You can see that there's lots of slope incompressible states here. I'm just going to tell you that essentially all of them have charge gaps in the range of like 0 to maybe 0.1 to 10 millivolts or so. So right in this range. Okay, so for a sort of greedy PhD student who's looking for a postdoc and thinking about what sort of experiments might be interesting to do, you can see this and say, well, it looks like there should be tons of sort of interesting ground states to look at. They should have sort of, maybe you might think about interesting collective modes to probe on this energy scale as well. Okay, now of course, it's not so easy, and I wasn't quite that naive getting into this. But there's always this big problem, and you've probably heard this argument 100 times by now, that for van der Waals devices, of course, the size of the device is maybe tens of microns at best if you have a really homogeneous system. In practice, if you're looking at a Moiré system with severe twist angle disorder, you might want to focus on a tiny region, maybe just a few microns or less. Okay, and so what the hell are you going to do with this diffraction limit? At 1 terahertz, the wavelength is 300 microns. It would be a fool's errand to try to do sort of typical far field terahertz spectroscopy when your spot size is 300 microns, but you want to probe something that's on the micron scale or less. Okay, and obviously this is a well-known problem, but people have been beginning to develop some really promising schemes for addressing this. And what I'm going to mainly focus on in this talk is a variant of something that I'll call this sort of on-chip terahertz spectroscopy, which, to my knowledge, was first used by Feng Wang's group to sort of probe, talking about applications to van der Waals devices to probe graphene. It's been extended by a few different groups since then. And so in this scheme, basically the idea is to, now instead of trying to do spectroscopy in free space, let's do all the spectroscopy on the sort of substrate itself. Because what we can do is then confine the terahertz fields into a transmission line, which is sort of drawn here, okay? And there's technology that exists that allows us to generate and then detect terahertz transients on the chip using ultrafast lasers, okay? And so this looks like a really, promising scheme, and this works very nicely for graphene and for some materials. But I want to point out that even if you go ahead and do this, even if you make a nice Moiré device on a sort of transmission line and then go and try to measure the terahertz conductivity using this scheme, that's not the end of the story. You're going to run into some additional problems, okay? So let's imagine for a moment that the device that we want to measure is electrically short, by which I mean short compared to the wavelength at terahertz frequencies in that medium, okay? So that means that I can sort of treat the device as a lumped element in some circuit. And what does the circuit look like? Well, it depends a little bit on your transmission line geometry, and you need to be careful where you're working in the time domain or the frequency domain. Doesn't matter. At the end of the day, the circuit that you're really measuring this device through is going to look something like this, where you're sort of connecting it just in the middle of some transmission line that I'm going to say is characterized by some characteristic impedance Z0, some length, and some complex K vector, or if you like, you could call it a propagation constant, K. Okay, and so at the end of the day, again, however you measure this thing, you're going to end up with an equivalent circuit that looks something like this. Okay, where in effect, to get any effect from the sample impedance on the overall circuit characteristics, you need to be matched to the characteristic impedance of the waveguide. Okay, and this turns out to work pretty well for graphene, and that's why there were some of these nice studies done in the past. But I'm here to tell you that this is quite difficult to apply to TMD systems, especially Moiré systems, where first of all, the sort of sheet impedances that are involved tend to be large. And of course, this is the sort of total device impedance, right? I can always change it by changing the geometry, but if I try to make for example, a Moiré device very wide to try to tune this, that's not going to work. We're going to end up with a really inhomogeneous system. If somebody knows how to make a homogeneous enough Moiré, please send me an email. Good. And that's not the only challenge. Maybe another huge challenge with this is that graphite gates are a big problem in this scheme, because you can think that adding a gate here is just going to go in parallel to the impedance that you want to measure. And maybe the last complication I'll mention for now is that, okay, this picture is sort of simple to analyze if the device is electrically short. In practice, you'll often find yourself in a regime where it's not electrically short, where we actually have to treat the sort of the device itself as a transmission line. And I'm going to show you a concrete example of that in a couple of slides. Good. So as I just told you a slide ago, I used to do scanning SET, and so it's really hard to go back to doing globally average measurements after doing scanning measurement. So what I'm going to demand for the next few slides is that I want a scheme that is not only local, but also layer selective in the sense that I can deconvolve or at least separate the contributions from a gate layer from that of say, some layer that I'm more interested in. Okay, and the way we're going to do this is by examining these excitons that I mentioned at the beginning. Okay, so June just nicely introduced the TMDs, and that's good because I didn't include too much introduction on these materials. I'm just going to show you what the device looks like. Okay, so on the left here, this is just a cartoon picture of the sort of device geometry that we'll be focusing on. So we have a van der Waals stack that's placed on top of some gold transmission line. This is not to scale. They're not really this thick compared to the stack. And the width here is on the order of 15 microns, and the thicknesses here are hundreds of nanometers. Okay. So in particular, we're going to be considering a case where I want to focus on the behavior of this tungsten selenide layer, because at least for us, we always find that this has the sort of nicest optical properties. And I also have a molybdenum selenide layer. You see there's no graphite gates involved. I'm going to actually just think of this molybdenum selenide layer as sort of acting like a gate for tungsten selenide. Okay. And so in this sort of on-chip scheme, which we're implementing here with a twist, I'm going to call this something like a terahertz pump and optical probe scheme. Okay, so let me first explain where the terahertz pump comes in. Okay, so upstream of the device, somewhere 100 microns away from the device that we want to measure, we have some photoconductive switch. Okay, that basically, in response to exciting it with an ultra-fast laser pulse, will generate some sort of terahertz voltage transient that will propagate along this transmission line. Okay, with a duration of about 2 picoseconds or so. Okay, then instead of directly detecting that terahertz transient using a second switch, which is what most of the schemes that I was describing have done, instead we're going to just use a synchronized optical pulse to probe the excitons of the TMD layer. Okay, and I should say that this is a sort of typical ultra-fast optics experiment. The sort of synchronization is just achieved by tuning a mechanical delay line to control the timing between the two pulses. Good. So let me first show you some kind of introduction to the optical spectrum in equilibrium of tungsten selenide. I just want to note that there are a couple of features that you'll see appearing over and over. So first of all, here I'm plotting as a function of hole density. Okay, so we'll only focus on the hole side of tungsten selenide, and correspondingly the electron side of moly selenide in this talk, because this is where the contacts work well. I should say that these are both contacted with graphite with some extraneous electrodes that are not part of the transmission. Okay, so what are the features that we have here? Well, at zero hole density, we have a neutral exciton that I've labeled X0 here. It has a relatively large reflectance contrast, which is typical of TMDs. Okay, and now as I start to dope the system, this neutral exciton evolves into two sort of features, one of them very weak, one of them a little bit more clear, that I've labeled AP and RP. And so RP means these are just names. I don't really want to explain or argue about the names, but they're just names. This is going to be the repulsive polaron, and this one I'll call the attractive polaron. And we don't need to know anything about their properties until maybe the last slide of this talk. So I'm not going to say anything else about them. For now, if you want, you can kind of think of these as charged excitons, if you like. Good. And so now the question is, what happens when I start to excite the system with this sort of terahertz voltage transient? Okay, so this is what the voltage transient looks like. Okay, so this is measured independently somewhere else on the device using a sort of second photoconductive switch, and so that's what this current means. Don't worry about the units. Just note that it's again sort of a couple picoseconds in duration. Now I'm going to probe the change in the reflectance contrast at this point in the transient. So in other words, about a picosecond after this transient arrives, at the device. Okay, and in particular, I'm going to focus on this quantity that I've named delta R over R. Okay, which is just the difference in the reflection when the pump is on versus off, which we can modulate very quickly using a mechanical chopper normalized to the reflection we get when it's turned off. Okay, and so then the result of this sort of calculation, or this quantity, is shown here. Okay, and so what we are seeing is that there are relatively large changes in this spectrum. First of all, we're seeing changes of 14%. The original sort of reflectance contrast here we get is up to about 50%. So you see that actually the terahertz field is having a rather large effect on the spectrum in the first place. Now, I also want to point out that you see that the changes are the largest at some sort of modest doping here, but they go to zero if I bring the system back to charge neutrality. Okay, so in other words, I have to have some sort of Fermi surface to get a substantial change in the reflectance. Okay, and so to sort of understand a little bit more clearly what's going on, of course, we have our delay stage, and the whole point of this is to sort of study what happens as a function of time. Okay, and so what I want to do now is focus on a few different densities and see if there is any sort of interesting dynamics that appears as I change the delay time. So I'm going to start at some low density here around 0.4 10 to the 12. Okay, and so we measure some spectrum of this dr over r quantity as a function of time. Okay, and what you see that there's some sort of slow relaxation that takes place over more than 15 picoseconds. But what you may notice is that there's at some time after the pulse arrives, there's some peak in the response. Okay, and that's what I've just labeled with an arrow here. Now, I'm going to now check a slightly higher density. Okay, if I go now to 8, 10 to the 11, then I see that I again see a peak in response on this repulsive polaron, but it becomes a little bit faster. Okay, instead of being at like 4 picoseconds, maybe now it's at 2 picoseconds or so. Okay, and if I increase this even more, then I see that this response, this peak in the response just seems to get faster and faster, which feels a little bit suggestive of sort of maybe that there's some propagating mode that we are picking up with this technique. Okay, so if we think something's propagating, we can do a really obvious technique to check that. We can just probe at different positions, okay, maintaining the same sort of synchronization between the pulses. Okay, so now I'm showing you at fixed density, the same measurement just at 3 different positions. Okay, so in this geometry, I'm injecting the terahertz field in some sense from the right, and then we sort of expect that it will then somehow propagate from the right to the left. So I've labeled the right as z equals 0. The left is sort of the left electrode is at 15 micron. Okay, so if I probe really close to the right edge, then I see some relatively fast response, faster than 2.5 picoseconds. But as I move farther away, 5 microns and then 9 microns. So the peak here, first of all, this feature weakens a bit, but you see that the peak gets later and later, which obviously is a clear sign that there's some sort of propagation. Okay, so to avoid just plotting tons of spectra at every point, I'm going to basically define some just simple quantity that I'm going to call little r of t here, which all I did is just take the absolute value, integrate over the sort of resonance, and then normalize these. Okay, and so this sort of really clearly shows that at the different positions, the sort of peak obviously is getting later and later. Okay, and so now this kind of lets us take a sort of image of this, whatever this propagating mode is, at different densities. Okay, so if I check again, this 4, 10 to the 11, the same density, you can see that there's this, we see this blob that goes across in about 8 picoseconds or so. Okay, and as I increase the density, now it becomes very clear that this thing just, the velocity becomes faster and faster as I sort of increase the density. Okay, so we have some kind of blob that's going across the device. But what's a little bit surprising about this blob is that it might not be immediately apparent to associate this velocity with maybe the most familiar features that we might think of in the tungsten selenide, right? So you might ask, well, what's the velocity of the terahertz field propagating on just the transmission line? And the answer is it's about c over 2.5, so something like 10 to the 8. So that would be 100 microns per picosecond, right? What we're seeing here is much slower than that, right? I'm going about 8 picoseconds, 15 microns. The velocity is on the order of a micron per picosecond or so. So it's something like c over 100. Okay, but this is still sort of faster than the Fermi velocity or any certainly any like phonon velocity in the system. Okay, so what's going on here? To answer this question, we need to take a closer look at the sort of electrodynamic modes that we should expect. Okay, and so let me just introduce let's just ask a simple question, which is if I have a single conductive interface, simplest possible model, only classical, Maxwell's equations, and let's make a simple assumption about the conductivity, then what are the transmission line modes? In other words, the plasmon modes of this conductive interface. Okay, and so in a certain high frequency limit, you can get a pretty simple expression for the dispersion relation, which is given by this, the K vector here, and some conductivity, which I'm also for now assuming to be K independent, for this whole talk, assuming to be K independent. Okay, so just to get some intuition, let's just plug in a Drude model for the conductivity. Okay, we get the usual thing. And I like to think about impedance, so I'm going to phrase this as a sheet impedance. And in particular, I'm going to define this quantity, the kinetic inductance, okay, which is analogous to a kinetic inductance that maybe you more commonly hear about in the context of superconductors, basically the mass divided by the density. Okay, and so if I phrase everything in terms of this kinetic inductance, then the sort of the complex wave vector, has this very clear dependence on epsilon times the sort of kinetic inductance, which if you like is sort of like the epsilon times the permeability for a photon. Okay, so what's interesting is that this kinetic inductance for materials like tungsten selenide, it's relatively large. Okay, and so if you plug in the numbers, you'll find that this is enough to really substantially suppress the wavelength and give you a corresponding reduction in the velocity. Okay, and so just to be clear, so this is a figure I copied that was focused on sort of surface plasmons on metal surfaces, but the intuition is the same for this sort of 2D system we're looking at. You can just keep in mind that the mode we're looking at is basically it's a transverse magnetic mode. So it's fully characterized by a single field component, this HY, that points transverse to the propagation direction, while there's a small sort of longitudinal component of the electric field. Okay, and so what I want to do now is ask, well, okay, what if I solve for this mode in the 2-layer system that's more suitable for the actual experiment we did, because we still have this moly selenide gate that's floating around. Okay, it turns out that the picture doesn't change too much. What happens is that you get a new mode. Okay, so basically there's two modes. So there's what I'll call the optical mode, which is terminology that was taken from some earlier works, that goes as root K, and this is the same, in effect, the same as the mode that we had on the previous slide. It's kind of as if basically the currents are flowing in phase on the 2 layers together. So it's essentially very similar to the sort of single layer mode. Okay, we also have a new mode, which I'll call the acoustic mode, that goes linearly with K. And what you can see is that in general, this acoustic mode has at a fixed frequency will have a much larger wave vector than this sort of optical mode. And I'm plotting this just for the same densities that we looked at in the experiment. Okay, so you might want to know what do these look like? okay? Especially with an eye toward sort of application. This is the optical mode. So here what I'm showing you is sort of a side view, okay? Just as if we were looking side on to this exact structure and exciting it on the right. And I'm plotting this, again, this single field that characterizes everything, just this HY component. Okay, what you see is that this sort of penetrates relatively deep into the substrate. This is on a micron scale. If I zoom in and look near the device, you can see that there's some contribution from both of the layers. And I can calculate the sort of surface charge density that's associated with this mode, which is at a fixed frequency on the two layers. And as I sort of alluded to, they're in phase for this optical mode in the sense that it's similar to the sort of single layer case. Okay, things are a bit different for the acoustic mode. If you zoom in, first of all, you see that the field is really tightly confined here. And if you zoom in, you see that the charge is out of phase on the two layers. Okay, so this one's sort of more effectively confining the field in the optical. Good. So what's the point of this discussion? The point is that I'd like to identify the sort of mode that we see in the experiment, and we can do that pretty straightforwardly just by comparing the velocities that are measured with the sort of predictions of this model. So we can just calculate in this case, the real part of the group velocity, and we get a plot that looks like this. So there's a lot going on here. These upper traces are the optical mode. Okay, the lower ones are the acoustic mode at each of the three densities that I took as examples. Now, the horizontal dashed lines are the measured velocities from the experiment at each of the corresponding densities. And you can see that they only overlap with the optical mode and not at all with the acoustic mode. And in fact, the sort of stars indicate the frequency at which the mode velocity calculated agrees with the experiment. You see that it's very close to the spectral weight of the pulse that we measure. Okay, so anyway, this is just to say that in effect, it looks like we can image this optical mode using this sort of technique, which is sort of interesting because in some sense it's terahertz imaging is usually not such an easy thing, but this gives us a sort of way on the nanometer or at least few hundred nanometer scale to sort of image dynamics. Okay. Let me just, I want to go through one other thing, but I'm sort of running out of time. I just want to quickly mention that we think, the mechanism is sort of easy to understand. It looks like since we have this charge density modulation associated with the mode, we already know from the equilibrium reflection contrast that changing the density should change the reflection contrast. And so you can kind of think that what we're doing by generating plasmons and injecting them into the system is just sort of wiggling the local carrier density a little bit, which moves us on this plot and then generates a small change in the reflection contrast. Okay, I'll just tell you one other thing before I go to high magnetic field, which is that we don't see any of this if we just do a normal terahertz transmission measurement, right? So this is puzzling and in some ways disturbing, but that's why we started doing this. We made tons of devices, tried to measure transmission, and we measure nothing. And so what I hope is that this will sort of give us a new way of probing these dynamics that might be very complicated or difficult to pick up using this sort of more conventional technique. Okay, finally, let's get on to what happens at finite magnetic field. Okay, I showed you this before. This is this plot of density and photon energy at zero magnetic field. When I turn on the magnetic field, not a lot changes except that we start to see these sort of oscillations in this repulsive polaron feature. Okay, and this isn't something that's even necessarily associated with the terahertz pump. Okay, this is a work from the ETH group. So in this group work, there's no pump. They're just measuring reflection contrast at high magnetic field, 16 Tesla. This is molybdenum selenide. And they see some similar wiggles in this sort of what they call the exciton, which is the same as these repulsive polaron. Okay, and so what this shows is just that the presence of Landau levels in the spectrum sort of induces some modulation of the sort of equilibrium reflection contrast. Okay, so there's nothing new here yet. What gets a little bit interesting is that if we now examine the dynamics again, varying the delay time, okay, I fix the density here, again, at the same number, 4, 10 to the 11. What you see is something very different from what we saw at zero magnetic field. Now, suddenly we see some sort of nice coherent oscillations that take place, actually with no sign of propagation anymore, right? And so probably if you see this, you immediately think, well, this is very likely the cyclotron resonance somehow that's picked up by the exciton. right? And this seems to work very well. We can Fourier transform this. We can check different densities. We get something that's, very linear with respect to magnetic field, as it should be for cyclotron resonance of a parabolic band. We can extract an effective mass, which curiously comes out a little bit lower than what is usually reported from Shubnikov to Haas, but I won't dwell on that unless anyone's really interested. And let me also note that as it should for cyclotron resonance, we can, so for TMDs, we can sort of selectively probe different valleys by using circular polarizations. And we find that this is purely intra-valley, so there's no sort of funny valley oscillation taking place. So it looks consistent that this should be cyclotron resonance. It's then a little bit confusing to ask what could the mechanism of this be? Of course, we would be tempted to first think, well, maybe it's some propagating feature, just similar to what we saw at zero magnetic field. But we don't see any sort of similar propagation delay. In fact, we just see that we don't see anything sort of delayed in real space. We just see that everything, it just sort of globally turns on at the same time, almost instantaneously. So it's kind of like just an instantaneous global field in some sense. So you might say, well, maybe the sort of the input pulse, maybe there's like just a huge absorption, and maybe the input pulse itself is sort of oscillating macroscopically at this omega c, but we don't see again any change in the terahertz transmission. And maybe I won't dwell on all the details here. What I want to tell you is that maybe a more plausible mechanism that was even previously seen in gallium arsenide is that maybe we are sort of actively repopulating Landau levels to a significant degree by the effect of the pulse. In other words, the pulse comes in, promotes many electrons to some other Landau levels. In some way, this would be analogous to the Rabi problem, but of course now we don't have a two-level system, we have a many-level, we have a ladder. And so there's really a huge phase space for these transitions. These are a couple of works that were done in gallium arsenide. I will tell you just that this is using a relatively low driving field. And despite that, you can still sort of get these oscillations quite easily. Okay, and so just to put a tiny bit more meat on this, there's sort of, what's new here is that these works, they're basically just detecting the sort of transmitted field through some big piece of gallium arsenide. It's not at all obvious why this cyclotron resonance should show up in this exciton, which is of course probing in some sense probing a much higher energy scale. Okay, but we can. So first of all, there's a theory work, and then I'm referring again to this work on the equilibrium reflectance contrast in the presence of Landau quantization. The takeaway that I want to give you here is that let's consider some broadening of the exciton line that's controlled by the Landau level populations. Okay, and forget about the time dependence for now. Let's say that there's just a term that's basically rho n, which I'm saying is the population in the nth Landau level, which can be anywhere from 0 to 1, times 1 minus rho n. Okay, so this is 0 whenever the Landau level is filled or empty. Okay, this is very consistent with this sort of equilibrium modulation of the exciton line width, right? Because we just see some sort of periodic change in the line width, which they analyze in detail in this paper. What I want to do is basically, and I'm telling you that you can get this sort of by doing some more theory. Our theorists did it. I didn't do it, but I'm just telling you that this is plausible. Let's promote this then to have time dependence. Okay, so if we promote this to have time dependence, then suddenly we get a situation where the line width of the exciton changes in real time in response to the repopulation of the Landau levels. Okay, so there's sort of a perturbative coupling between the exciton and the Landau level populations. And then the Landau level populations themselves can be sort of calculated by solving the Heisenberg equations of motion sort of directly. And for this to be plausible, you need to make sure that the Rabi frequency isn't too low, and it actually turns out to be pretty large for the specific parameters that we're using. So this kilovolt per centimeter is the common unit that's used to describe field strengths in this field, and we're always sending fields here that are a few kilovolts per centimeter. So this is right on the order of the cyclotron frequency. So it looks like this is sort of consistent. But I think I should, basically leave it there. I'm not even going to read any of this, but I just want to tell you that, it looks like we should be able to apply this to a variety of interesting systems. There's discussion these days about, fractional quantum Hall effect. fractional quantum anomalous Hall effect and twisted Moly Telluride. Fractional quantum Hall effect is interesting too, but maybe. But in particular, this fractional quantum anomalous Hall state is supposed to have this magnetoroton mode, which has been discussed recently by Liang Fu in some works. And this is interesting because in the old story, fractional quantum Hall, gallium arsenide, say, you never see this magnetoroton very easily. You need to do some sort of complicated Raman experiments. And I wonder if that might be easier to find in these Moiré systems. One other possible application that I'll just mention is that there's now a very nice systems for studying exciton insulators and sort of possible exciton condensates in electron hole double layers made from transition metal dichalcogenides. It was done in our Cornell group and also Wang's group. It would be really interesting, so these show a really nice sort of perfect Coulomb drag, and it would be really interesting if we could eventually probe excitations of condensates or sort of superfluid states in those systems, but of course that remains to be proven. So I think I'll leave it there, and thanks for your attention, and happy to take your questions.
So in terms of the double layer, like the ground state exciton, I mean, naively, there's no dipole, right? I mean, nothing gets excited.
You would need to excite out of the plane. Yeah.
Out
of the plane, yeah, an out of plane. You need an out of plane electric field. No. Surely it has it doesn't have a dipole moment out of the plane. It has a dipole moment out of the plane.
Well, I mean, it has a permanent dipole out of the plane.
Yeah.
But that's not what will couple to the Telluride light.
Right. So then you couple to some sort of longitudinal, maybe some modulation of the local exciton density. That's what I would think.
Okay, I'm thinking of the in-plane transport of the ground state exciton. If they always bind together, then they move together, then it doesn't respond to an in-plane.
Right. So I think you need both. And I think you still need some sort of out of plane electric field to modulate this thing. Maybe you need, I don't know, maybe you need some sort of background charge on one of the layers. Like maybe it doesn't work precisely at neutrality. I'm not sure.
That'll be completely symmetric.
I see.
What's temperature?
This is all 3K.
How much does it turns like this is?
So we've checked up to like 10K and we don't see any significant changes. You do start to see the cyclotron broadening a bit, maybe around 10K. Otherwise, no significant change. Yeah.
Did you try calculating the plasmonic modes with a magnetic field? Because this may be gapped out.
Yeah, it is gapped out, and okay. so you basically get the mode turns on right around the cyclotron frequency, but the velocity is similar to what you get at zero magnetic field. So I would have thought that we would see some propagation effects if there were a magnetoplasmon. Yeah.
How large is the gap? Maybe your
frequency. It's exactly the cyclotron frequency. Yeah. Sorry.
Yeah.
Oh, great. Thank you.
Thank you.
There's a quick break and you have
half hour help, right? So 4. Yeah.
At 4.
Or sorry, let me oh, it is, yeah, we're running early. So cool.
Okay, so we have almost 45 minutes.
Yeah, like RPA so you were able to reproduce the VMs, like the VMC production entities of Polaris of them.
Okay.
That's what they claim, but there are some caveats.
Okay.
Essentially,
I think so because I think Coherent that
on like charge modes.
What do you measure? What's the
One device 0.31, the other one's 0.4 something.
I mean, so. I see, so it's sort of an arbitrary choice that maybe was problem specific, yeah.
Yeah, so I can tell you more about that.
Yeah.
But, you know, I also, you know, is there any?
Taking over.
Well, if you.
I can do it.
But sure, yeah. I'm sorry. I can just.
I have it. I need like I'm using my I have to.
Every time you took a picture, I felt like I should take a picture.
All right, continue, these sessions, so, pleasure to have, Judy from, Stanford and CCMIT, telling us about, 3D Twistronic platform and a fractional physics.
Thanks. I'm gonna use this very old school stick, right? Yes, here's the outline. I'm gonna combine two parts that are not super relevant, but I think relevant to the topic of this workshop today. And I'm gonna start with the 3D Twistronic platform. So I think the speakers before me, like June and Andrew, have had a really good introduction to the TMDs and twisted TMDs. But then essence is that when you have twisted by layer in this toy model, you can think of this as having a little bit of mismatch between the k-value in the top layer and the bottom layer. And then when your twist angle is very small, then this
What's for? I'm sorry. The bell was 15 minutes. The coffee break had started 15 minutes earlier than it was supposed to. And it ended 15 minutes earlier than it was necessarily supposed to. So let me bring people in from outside.
You understand?
I apologize.
My fault.
There don't seem to be stragglers. I wait. Yeah, please continue.
So when your twist angle is really small, so unlike the graphene case, you have a magic angle here in a continuum of angles. You'll have a very small bandwidth for the topmost valence band or maybe the bottommost conduction band due to this band hybridization. So this is the way to look at it in the case space. But anyways, so all those have contributed to getting a plethora of correlated phases in the twisted TMD systems, like superconductivity, like XAI, among many others. So when we saw this early results coming out, we had a question like, what would happen if this twist is not only happening in 2 layers, but in multi-layers? Well, at that time, there were already some proposals, theoretically, of the moiré of moiré. Namely, if you have moiré in between layer 1 and 2, and also in between layer 2 and 3, then you will have different integer combinations of those moiré cells, and you can get those moiré patterns, as Ben was talked about this morning, with larger length scales. But actually, an extreme case of this is not that you have 3 layers stacked together, but you have a 3D stack out of it. So this is like stacking graphene back to graphite and the TMD back to above TMD. There was some discussion with our theory collaborator Zoe, it's now at Stanford and soon at Boston College. So through some modeling, one can say that in the 3Ds continuously twisted TMD, you will have quasi-crystals formed. If the twist angle can be divided by 360 or 180 degrees. So namely, when you have theta equals to 10 degrees or 20 degrees, you will see this type of like orderly disorder happening in this system. And then when you have very small twist angles, I don't know if you want to see it clearly, but there will be some more patterns. That's as expected. So one can think of it as having this like one layer, that layer would form with sense the potential or potential coming from the layer up and one layer down. And then you have a lot of those units to form this 3D stack. So then here, KZ becomes a good number. And yeah, what's more peculiar for this case is that actually when you stack it to 3D, you will find flat bands at certain KZ values. And there were also through some C2 calculations for Z topological invariant calculations, there were some topological invariant changes from trivial to topological when you change KZ from a small number to a larger number. So this might remind many of you that this could be a configuration of forming a 3D Weyl with 2D Chern isolators and trivial isolators. But there are other possibilities like 3D Chern isolators, among others. So there was also another theoretical proposal from Sankar Summers group, and they found that if graphene is continuously twisted to form a 3D graphite, then it will have a type 2 Weyl fermion in the system, and also there will be several orders of magic angles at which you will have flat bands. And this type of flat bands have slightly different consequences, although those are all like simple particle calculations, but it's expected to have different consequences as respects in comparison with the 2D cases, including those consequences in its related ground states. So I would call for more theoretical understanding of the system, because right now it's mostly still like simple particle.
So in this point, when you say
Yes.
KZ, so the brilliant zone in Z direction is very, very small, right? It's include periodicity of your pitch.
Yes, that is the case. Yes. And the regular block wave function has to be considered in this twisted framework. So, yeah. And then finding the material platform was actually quite of a huddle, because just by like manually stacking it layer by layer would be a waste of graduate students' time and more or less not possible, because this is like so many layers. But it turns out our collaborator at UWM has this special technique of directly growing super twisted stacks of TMDs. And the way that they do it is through growing on a non-Euclidean surface. If you have a water drop on your surface, for example, and you do a chemical vapor deposition growth, then you can find something that's continuously twisting, and then the twist angle between among the layers is always the same. So that's exactly the system that we were looking for. And because the thickness can be very large, so it really forms this 3D criteria. And so there are large length signal modulations that they found in the STM studies. You could say that these are probably the unit cell and the Moré patterns, and they also have this Moré automodes. So yeah, with this system, we were trying to figure out what is a good way of probing its geometry and topology. It's 3D, so it's very hard to gate it to do like full electrical control. But we wanted to utilize something related to the property that is a semiconductor. It has excitons. It is a TMD to visualize it. So this is a recap of the anomalous Hall effect, which is what people usually use for study the 2D systems. And if you have a broken time reversal symmetry, then this anomalous velocity term will give you a non-zero integral. And that is as if you are having a magnetic field to give you this transverse Hall current. And through measuring this, you can get a good understanding of those 2D systems, especially its topology. Well, but there's actually another variant of it. If we are not sure if we have broken time reversal symmetry, but we have broken immersion symmetry, for example, and if the system has well established like those like valid degrees of freedoms, then one can actually trigger this valley Hall effect with circularly polarized light. And here what you do is you populate selectively some carriers in one valley by only exciting with one circular polarization of light. And that is determined by the selection rule. So for example, if we have a left circularly polarized light, then we selectively excite this K valley. Then we can selectively also like get access to this omega of K, this Barrett curvature inside this valley, but not the other. So then here, even if you have a time reversal symmetry preservation, you can still get a non-zero Hall result. But yeah, certain symmetries will forbidden it. Maybe for example, if you have a 2H stack, then you have two copies of these bands, and then this valid degree of freedom does not work anymore, then you shouldn't be able to get any Hall effect even when you use circularly polarized light. So we try to use this as a tool to study our 3D system, just because we wanted to know a little bit about the topology or geometry or anything related to that. But it was actually really difficult to make a device out of it because of a lot of different reasons. One is that it's a TMD system, so making contact to make transport studies is very hard. After a lot of like failures, we finally used the method of using a semi-metallic electrode, which is bismuth, made out of bismuth, to make this 4 electrodes and etched it into a Hall geometry. And also another difficulty was that this super twisted sample is so easily relaxing back to AAA stacked TMD. Whenever you have mechanical shock, it will relax back. So one has to be super, super careful that in the whole process, there's nothing like shocking it. So we made around maybe 100, 200 devices, and a couple of them worked. And yeah, after that, I decided not to do any 3D devices. In the semi-twisted samples, what we found was we could actually see a Hall effect. And also this sign, so we excited at the vicinity of the excitonics resonance. And then this sign would change with the handedness of the light illuminating. And so that's to say that there's some contribution to this Hall effect that is determined by how these layers are glued to each other. It couldn't be just a simple sum of all the monolayers valid Hall effect signal, otherwise it won't change its sign. So there's a term coming from those. And then we digged into the details of that Hall effect. There's a bit of jump here, but we directly measured this momentum dependence of this Hall effect. Like yesterday I discussed was hard, and I think many theorists know that for example, the Landau levels, there's the Kong's theorem, but also there's the Houdin limit, which means the sigma xx, the optical conductivity or intra-band ones, have this q to the fourth, the momentum to the fourth dependence, instead of the q to the second. So because of that, we also wanted to say what can happen in our system. So instead of just like fixing this incidence angle of the light, we tried to vary the momentum of the light to say how this optical conductivity or this Hall conductivity changes with it. And what we found was that it actually depends on twist angle. So I'm selectively only putting on two eta here, plots here. When we have a larger twist angle, it seems like we can get a very smooth sinusoidal curve as a function of the incidence angle theta. That's to say, it has a somewhat of a zeroth or first order dependence on the momentum of light. But when we go to lower twist angles, this curve becomes sort of weird and it has like higher order contributions to it. And this was consistently found in a bunch of survived samples that it seems like the momentum is playing a significant role in this conductivity in the system. Well, how do we understand this problem? If we think about optical transitions as coming from one wave function at k to another wave function, connecting these two wave functions by the velocity matrix at k plus dk by the q, so that's the momentum conservation. Most of the cases, the q is negligible. But here, for this mini Brillouin zone, it's non-negligible. So in the regular Brillouin zone, one can think of this photon causing a shift of charge center. That's a second order optical response that you can imagine that causes the shift current or this whole conductivity. But in this mini Brillouin zone, you not only have that, but you have access to the shift of multiples. And you're no longer in the limit where the plane wave approximation works very well. The shift of the charge center would give us access to all those like Hall effects or the nonlinear Hall effects. So that's the Barry curvature dipole or Barry curvature itself. So anomalous Hall effect, Barry curvature itself from the intrinsic component of it. But then for the shift of multiples, you actually have higher order multiples in this excitation process. So this is not exactly what the motivation that we started, but actually what we observed in this system, such that the light matter interaction was really altered in the process when you have a system with the Moiré or Moiré modulations in it. In a different way of talking about this, so that's in this momentum space. I can also do it in this real space. In the real space, the way to think about it is that, oops. Not as hard as making that device, so that's okay. Yeah, a way to think about it in the real space is that, well, we're now in this Taylor hall, and it is relatively short. That's as short as the electron wave function, or this like periodicity of this Brillouin zone. But then the photon, on the other hand, in the visible regime, is on the micron size. So the difference between these two is huge. And most of the cases, this is considered negligible. It's not always the case. If somehow you expanded it to a size or a height of a mountain, then you really need to consider that. A very classical example of putting the electron and the photon on the same size is by shrinking the photon. And that's a whole field of plasmonics. But here, instead of shrinking the photon, we expand the electron. So here, I don't know if I can play this, but okay, yeah. The idea is that when your twist angle becomes smaller and smaller, when you have the Moiré modulations, you can think of it as a photonic crystal now, and then the light matter interaction got altered because of it, and we call it the opto-twistronic Hall effect. So yeah, the reason I put this first half here is just because this system is potentially topological from the theory. So I would hope that there will be new experimental tools or theoretical inputs to understand better what will happen in the theories. Okay. And let me go to the second part.
Sorry, can I ask, so
Yes.
where is the chemical potential in the band structure?
Yes, then the chemical potential would be more or less inside the band gap. So we excite excitons instead of directly measuring the transport as of this reason.
So the theory prediction is that the occupied band, the topology.
The theory prediction is that the whole structure will become a biosimilar. And the ultra flat band is also another prediction. So these two are, two predictions of them. And for the graphene system, the ultra flat band only happens at specific magic angles. For TMD, it should be pretty much a large range of twist angles. We weren't able to really access this information yet in this study. We hope to. Okay. I'm not stuck again. So let me see. Okay. Okay, so the next part is a continuation of June's talk on the fractional Chern insulator. And from the edge state perspective. So an edge state of an integer quantum effect, it can be explained in this single particle picture, where you have those confined potential at the edge, and the bending of your Weyl level would make the Fermi energy cutting through different numbers of that discrete bands, and how many bands you cut through determines how many edge states you can see. And this has already been observed through nanoswit and other studies. But in the case of fractional quantum Hall effects, it's more complicated because of the electron-electron interaction. So then, for example, theoretically, one can think of it as a chiral liquid. And because of the particle Hall symmetry, when you have those like hole-like states, like the nu equals to 2/3 state, it cannot directly be adjacent to nu equals to 0. So somehow the edge has something complicated going on. And these are some of the possible models for the nu equals to 2/3 edge. The Verma model showing the downstream and upstream mode, the KFP model including the scattering between the modes, and then the mirror picture adding 2 more counter-propagating modes. Yeah, there are some early studies about the fractional quantum Hall edge states. One is the magnetoplasmon resonance, when you use one electrode to inject a microwave pulse, and then you measure at the different electrode, like Hendrik's experiment in the microwave regime, where you can see this type of oscillations, and that oscillation can tell you which direction or which chirality is it propagating in. You also have the noise measurement, having access to the neutral mode, also edge state interferometry. This is more for manipulating the edge states for quantum information and other possible applications. But yeah, we asked this question, how can we directly image the edge states? Well, normally it's difficult to image the edge states for technical reasons. For example, the quantum wall or 2D materials based fractional quantum Hall effect has ultra low temperature where it survives, and also very high magnetic field. And has specific requirements for this technique that one can use to image it: spatial resolution, sensitivity to bulk edge differences, and ideally you don't want direct electric contact. But all those just made the image relatively difficult. But as Jun just mentioned, this twisted MOT2 has been manifested as one of the two very good platforms for realizing this fractional Chern insulators. And through their measurement, one can tell that this type of fractional quantum non-Sol effect happens when you have 2/3 filling of all those gene sequences, and also happens at displacement fields equals to 0 or close to 0, where the two layers are strongly hybridized with each other. So we thought that maybe imaging this fractional quantum non-Sol effect might be easier than the fractional quantum Hall effect, just because the gap is larger. That means we don't need to go down to very low temperature to do it. And also, it doesn't require a large magnetic field. So we use this technique, so-called the microwave impedance microscopy. Monica will talk about this more later on. I will just give a very brief introduction because of that. The mechanism here is you shine gigahertz wave, instead of terahertz, it's gigahertz wave onto a metallic tip, and this metallic tip hover on top of the sample. This tip sample interaction can be seen in the lumped element model. And the lumped element model works pretty well here because the frequency is considered very low. So then there's a tip sample impedance in the capacitive coupling regime. And this is what happens in the sample. So the sample has certain conductivity or resistivity, and then that can be reflected in its reflectance of gigahertz wave when we measure outside of the fridge. And the metallic tip allows the spatial resolution to be super good for this measurement, which is below 100 nanometers. So this is how this response curve looks like. So from here on, I will probably just say that if you see a larger signal, that means it's very conductive. So it's like a local transport measurement. The sigma XX is very large. Then when you see a small MIM signal, it means that this underneath sample is very insulating because of this response curve. We're focusing on this in that inner part. Okay, and then we use the transparent TMP top gate in order to make sure that the microwave can penetrate through the top gate to reach the sample region. And the key here is that we want enough carrier density, but small enough mobility so that it does not screen the microwave completely. And then we use some excitonic resonance to further decrease this or enhance this whole regime of voltage will indicate the sample. Okay, with all the tools and the samples, we can directly get into the data. So this is what just showed just now, the transport data. And this is with the newest generation devices, where one can see a more prominent feature at close to 1/3 and minus 1/2 those charge density wave states. And here is the MIM result. So the MIM result has a good correspondence with that. Including here at close to -1 and d equals d small d, one can see an insulating regime. So this is inside the bulk, and this insulating regime directly corresponds to here. We also saw the close to -2/3, close to -3/5, and those would correspond to some of these fractional Chern insulating states shown in transport studies. And one advantage of measuring MIM is we have a very good sensitivity where we're not limited by the contact performance in a small new regime. For example, here is a zoom in of the regime close to 0, from 0 to -1/3. And we can tell that here are some charge density wave states at close to 1/3, close to 1/4, and close to 1/6. And apart from that, since it has always been a question, whether this system has a good particle hole symmetry. If we see the fractional Chern insulating state at nu equals -2/3, can we see another state at 1/3, as in the case of fractional quantum Hall effect? Well, from the specific sample, because the sample is very angle dependent, twist angle dependent, so there could be different phases showing up. But here at nu equals -1/3, at least from the strata formula check, we see that this state is not moving with magnetic field. So our conclusion for this sample is that the nu equals to -1/3, it is not a fractional Chern insulator state. It could be related to Chern density wave or some other things.
Rudy,
Yeah,
sorry, I do see the blue, if I only look at the blue color, it does shift a little bit to the left, right?
it's the red color, which is the insulating in this specific color map.
Oh, okay.
Yeah, sorry for the confusion. I should have included a color map here, but yeah. So one can see shift of this red region to the left for nu equals -1 and -2/3, but not for the 1/3. So that's the way that we checked it. Okay, and then we did the spatial mapping of the device. So we had a twist angle of around 3.2 degrees from June's like the theoretical operators result. This is considered the larger twist angle regime. And then, so this is a sample, how the device looks like. So the yellow region is the scan region, and the red region is the interface, the dotted line. So with the red dotted line, is the interface region without top gate. I got asked this a lot, but this was not by intention, but just because AFM Konig killed off the top gate over there. So yeah, we would also like to have separate control of the left hand side and the right hand side, but here it's not. But we also have a very well defined flick edge, so we mostly look at the physical edge of this and what's the behavior over there. Okay. We're going to check the integer quantum anomalous Hall edge states here in this dual gate control. We follow this green arrow to go through the nu equals to -1 state at d equals to 0. And then we scan the MIM in this region. And as you can see, as we go closer and closer to nu equals to -1, there is a bright stripe, this horizontal stripe, which is at the same region of the flick edge, but in the middle, it's dark. So dark means insulating, bright means conductive. In other words, this region is conductive, this region is insulating. But as we move away from nu equals to -1, this behavior disappears once again. So that's to say somehow this bulk edge difference develops near nu equals to -1, but disappears away from that. That is the signature of the integer quantum anomalous Hall.
Can you, so there's also a big vertical stripe there?
Yes,
Is that,
this big vertical stripe is that like the AFM cleaning scrapped out top gate region. So because the top gate is not there, so there the carrier density and the filling is different from elsewhere. And then, yeah, it's, okay, it just happens to be metallic or insulating. Then we went to the fractional filling regimes. Here we follow another green arrow from nu equals to -2/3 to nu equals to -3/5. And we look at this evolution once again. So as you can see, mostly it shows metallic behavior or conductive behavior. And then gradually, as we go into the regime of nu equals to -2/3, or into the regime of nu equals to -3/5, there is distinctive edge being bright and bulk being dark. Of course, as shown in this 2D map, there's some disorder pinning and everything going on, so it's not as sharp as ideally you will get. So this too marks the observation of this fractional Chern insulating edge states. But before we can claim it is really a topological edge state, we wanted to try to induce a topological phase transition and see how those edge states evolve. And we did do that through the displacement field. So that's the advantage of working with a 2D device, that you can apply a displacement field. And this is how this conductivity or the MIM signal looks like. So there's a phase transition, and then in the middle, in the bulk, that's insulating, and that large displacement field is insulating once again. The whole process of changing the displacement field will give us maps like this. So here at large displacement fields, it's insulating everywhere. On the other side, it's pretty symmetric. It's also insulating everywhere. In the middle, however, as you can see here, the edge is bright, the middle is dark. So that's to say, here we saw this topological edge states, but it's not likely coming from disorder or something at the edge alone, because here we cannot see it. Street view. Thank you. Another question I got asked a lot is the spatial homogeneity. Actually, we also struggled with it a lot. Like Zhurun has been providing great samples, but it's really demanding for us to get a perfect sample in order to see this distinctive edge and bulk state. So this is as hard as just the transport global measurement in order to see this edge state. Here for this very nice sample, we saw the region 1 and region 2. So here, I define region 1 and region 2. Having the twist angle disorder on the level maybe less than 5% or even less. But in some other cases, there will be larger disorders in twist angle because of strain, or also like the crystal quality and other things impeding us from seeing the edge state. And what else we can see, this is related to the Santos mean field path question. We also wanted to say if we can directly see this topological phase transition or the plateau transition in those fractional or interior quantum states. Right now, the spatial resolution is not enough to directly see those domains or the first order transition moment. But we can at least see that it becomes more and more inhomogeneous near the topological phase transition from the charge density wave state from this equals to minus 2/3 fractional translator state sample. And then we dig into the nature of the edge signal. Without going into too much detail, the width is larger than what we thought. And also, so we referred to this Monica's paper in 2023 that in this microwave regime, we can excite the edge magnetoplasmons. And then the edge magnetoplasmons has a resonance frequency related to the charge of that mode. And also it has a characteristic width sort of determined by the perimeter of your sample. So this width is not the 1/r decay of that Coulomb fraction, but it has its own characteristic width. So, but from this resonance frequency and from the intensity of our signal, we can get some insights into what is really conducting, or what are the edge channels here. For example, we can see that there will be two parts of contribution to the neutron to 2/3 edge conduction. One is the bulk residue conductivity, and one is the edge magnetoplasma. And then if we assume a simple edge picture, we just have the 2/3 edge, assuming we just have that, then it deviates from our experiment. And that deviation, once we look further into those like theory proposals for fractional quantum Hall effect, we found good answers. For example, the KFB model says that the charge mode would propagate with a dispersion with a correction term, this diffusion constant, which is temperature independent, for this fractional translating states or fractional quantum Hall states, where the different edges are interacting with each other to form both the bosonic mode and the charge mode. And this gives us potential for different types of edge state manipulation. If this is not a tear, but a gate-defined edge interface, we might be able to see a lot more. Since the left-hand side shows nu equals to minus 3/5, the right-hand side shows 2/3 at certain conditions. Then there are other questions about this material. For example, what is nu equals to minus 2? There have been multiple different theoretical proposals showing that it could be an intervallic coherent state, it could be a normal insulator, it could be a Chern insulating state, it could be a quantum spin hole, or all types of other ground states. So we also tried to push the limit of our gates to get to nu equals to minus 2, and we did the spatial mapping. At nu equals to minus 2, this is like smaller and the larger fillings. And nu equals to minus 2, vaguely we can see something lighting up at the edge, but this is not comparable or similar to the one that we saw at nu equals to minus 1. So whatever is happening inside the bulk is becoming more inhomogeneous. And so we're still trying to dig into what is really happening at nu equals to minus 2. And also the even denominator FCIs, as we could see a little bit of hint at specific locations of the sample, and nu equals to minus 1 have as a gap, but we need higher sensitivity. So everything is developing. We're upgrading our technique to millimeter wave impedance microscopy, which potentially allows us to measure this in the range of 0.01 to 0.3 terahertz. And this is a region where one can see the non-element models still work to some extent, and we can put the sample onto the photonic crystal to measure the scanning signal. So these are some preliminary scanning signals that we got from this type of method. But to keep it short, I think the idea is that we want to measure some frequency-dependent responses to get more understanding into the magnetoplasma modes, and also to get more understanding what is really happening at the edge. This is still under development. So that's a summary. I hope I'm still on time. We have this optically coupled MIM as a technical advance, and then that sort of enabled our imaging of the fractional translating edge states, and also the local probe of fractional translator bulk states. So with the separated information of the bulk and the edge, hopefully we can get more information and narrow down the phase space of this fractional states. There are more open questions we would like to work on together with transporting other techniques, like even denominator states, composite Fermi C, magnetoplasma, and so on. Right, thank you. I would like to end with acknowledgements. Presented stuff that I've been working on with ZX group at Stanford University and our collaborators from University of Washington, and NIMS for the HBN, UC Berkeley for theory support, and UMN for the sample growth for the super twisted sample, and UPenn for the optical Hall measurements. Thank you so much.
Great. Arbitrarily long for questions, given the timing mishap or is.
Maybe, can you, so with this microimpedance measurement, you can get the kind of the local, conductivity, but you also mentioned that and I think I kind of missed it, but you're saying that you can distinguish these different classes of nu equals 2/3 edges. Can you say more about like what, and you were saying, okay, it has to do with actually this dispersion of the mode and so on. So are you saying you're actually able to measure that?
Right.
This technique or?
Yes, so this technique normally just measures the impedance of the sample, which is measuring the conductivity.
Right.
But for specific cases, for example, if you have a 1D edge state, then the 1D edge state can form some gapless magnetoplasmas, which is not gapped out. And 2D and 3D ones can be gapped out in this frequency regime. So this specifically can give rise to some enhancement of microwave signal because of the resonances. So then it is measuring the combination of these two parts.
Yeah, so with your edge, the nature of the edge state measurements, is there any way to prove from these measurements that the edge is chiral?
it will be possible through microwave pulses if somehow the sample is large enough, or the velocity of that plasma mode is slow enough, like it's slow enough. It might be possible to drive the whole system towards the transition point. And then where the plasma modes will be very the slow. And if it's slow enough and it's within the range of our time resolution, then we can use pulse signals to see which direction it is propagating into. That's one way.
And so it excited somewhere and then look for a signal downstream.
Yes.
And then do the reverse experiment but then it could always go wrong. A long
It's,
path.
you can see the time lag.
Yeah, time lapse, okay.
So you mentioned these plateau transitions tuning displacement field. Have you looked at the plateau transitions between different fractional states just tuning doping?
Yes.
Is there, do you see anything interesting in doing that?
Right, we've always been doing that, but what we saw was that maybe the sample quality is not good enough. So as you can see in some of the figures here, as we tune from 2/3 to 3/5, there is not a spot that it actually goes to completely metallic once again. So yeah, we suspect it's coming from the with better quality of the sample, we shall be able to say more about that to transition.
Can you make any identification of the phases in the regime where transport measurement fails between 0 and 0.45?
With the whole phase diagram or?
Yeah, or just, along displacement 0, something like that.
Yes.
Right, it looked like there was a fermi liquid for a while and then an insulator inside there.
Yes, so what we saw was a bunch of charge density wave states, even at B equals to 0 field. And 1/3, 1/4, 1/6, they seem to like be there both at small d and large d. But at smaller twist angle, there might be a phase transition that would make the ground state different. That's also the theoretical predictions that I've said before that make the ground state fraction Chern state. So we haven't looked into that specific sample yet.
Yeah. Can you also go to the new equal 1 image? Can I take a look first before I ask?
Yes.
Okay. So there's a bright dot in the middle.
Yes.
And then you go to the next slide. It looks like this bright dot appears everywhere except in the 2/3. That looks interesting. Do you have any idea of that?
Yeah, that's a great question that I've missed before. So thank you for catching that. So I would first explain why there's a bright dot.
Yeah.
So that's a bubble inside the
Boron
stack.
nitride, like bubble in a stack.
Yes, a bubble in the stack. And then why it becomes insulating over here? It's
It goes up everywhere except maybe for 1 and 2/3.
That's interesting. Yeah, I don't know the answer for now. I would love to know more to say what we can say about the sample distribution of things.
It might be buried in the color scale, because if you squint, there's still some, but the black, you like lose contrast. You might want to like plot it as like a slice to see if it's actually there.
How this
It's quite dark.
But once you're black, like you lose contrast to changes, so.
Well, why it become black is the question, right? The thought if it's a metallic.
Well, it changes colors throughout.
I mean,
Yeah, anyway, just like I was just curious.
The scale is very.
I mean,
It's relevant to what happened to the defect in the FCI.
Yeah,
Or
that's-
all very interesting, yeah.
Yeah, that's actually a very interesting question. We were previously trying to say whether we can think of this as a quantum dot and we can charge it. And if we can access those like charging
So you're
state.
sure this is a bubble, not a, because your resolution is not enough to tell a 10 nanometer defect versus maybe 100 nanometer.
Yeah,
Are you
we're
sure?
pretty sure it's bubble just coming from the AFM image. But yeah, if we can create some local defects, it might be actually helpful because we're measuring the edge now is the 1D defect. Only if we can study 0D defect as well, it will be interesting.
I remember Xiaodong mentioned the 1/3 FCI a while ago, never saw the data. Okay, maybe this is more question to
The
June.
twist angle.
What is a twist angle? That one?
That one is on the smaller side, ours is on the larger side. So
That
ours
one
is
was 3.0 degrees.
What?
3.0 degrees. This one's 3.2.
3.0.
So it's there or it's not there?
It's definitely there in optics.
No optics.
Yes.
Have you done transport on 3.0?
Somehow we have just below 3.0 and just below 3.0.
So going back to this question, if you apply a field now, what, 1/3 or 1/4 or whatever, is there a field induce HCI?
Right, that's a great question. At least from this sample, we didn't say it up to 12 Tesla, which is the maximum field that we applied. From June's data, it seems that for 3.2 degrees, correct me if I'm wrong, the transition would happen above 12 Tesla. So if it's 2.6 degrees, then maybe we can see that 7 Tesla. So it's a bit of like a twist on dependence there.
Can you go to D-dependent map? Sorry, I'm still curious about this.
Yes, sure.
Oh. So this interesting discussion that probably we should, I think now we're on. So that's good. Let's thank Judy again. The next speaker is Boncat Allen from CSD. Two HDMIs. Okay.
So I'd like to thank the organizers for putting together this workshop and for inviting me to participate.
There's a microphone there. Oops. On.
Can everyone hear me? Okay. So these are the key players who contributed to this work. My graduate students, Leonard and Chen, have been developing a new scanning probe microscopy setup in our lab at UCSD. On the material side, Lingyuan and Qichuan have been leading our experimental effort on van der Waals heterostructures and Moré superlattices. And I'd also like to acknowledge fruitful discussions and collaborations with theorists Zhurun Grover and Dan Parker, who are faculty colleagues at UCSD. So one of our overarching goals is the development of new microscopy tools that can shed light on topological states of matter. Driven by advances in material synthesis and in theory, there have been a string of experimental discoveries of quantum analogs of classical Hall effects that have been realized in 2D electron systems and topological insulator thin films. And although a lot of the initial discoveries and foundational experiments were performed in semiconductor heterostructures that were grown using molecular beam epitaxy, the family of topological materials has recently been expanding to include many different types of van der Waals heterostructures. And scanning probe microscopy techniques have offered amazing insights into the real space nature of topological modes in 2 dimensions. In this talk, I'd like to talk a little bit about some new imaging capabilities that we have been developing to start resolving states out of plane. Okay, so if you're doing an experiment on a 2D material, why should you care about 3-dimensional imaging to begin with? So on this slide, I'm starting with just a simple schematic diagram of a van der Waals heterostructure. And while electrons might be confined to a purely 2-dimensional layer, for example, a sheet of monolayer graphene, they do exist in a larger 3-dimensional crystal. And therefore, states on different planes can influence the behavior of electrons on a given layer. So for example, surface disorder or charge traps could affect electrons that are buried deep below the surface. The presence of nearby conducting layers could screen electron-electron interactions or screen the disorder potential. Of course, there are even more exotic scenarios where there's expectations of excitonic superfluidity in strongly coupled quantum wells. And so because of this, it's very natural to at least try to develop imaging techniques that can start to look at the full 3-dimensional environment. So in my group, we'd like to take steps to offer a glimpse into the 3rd dimension by starting to resolve states out of plane 1 atomic layer at a time. And these are some of the motivating questions, or some of the questions that motivated this direction. So if you have a van der Waals heterostructure with multiple conductive layers, where exactly are the electrons sitting laterally and vertically in the heterostructure? Is it possible to do layer-specific imaging of topological states? How is the surface disorder potential imprinted onto different atomic planes at varying distances below the surface of the crystal? Is it possible to screen out charge disorder by selectively tuning the conductivity of different layers in your heterostructure? And finally, can we study the interplay between various exotic topological or superconducting states with the real space disorder landscape or the screening environment? So this is will be a technique-driven talk. So we've been interested in developing a suite of complementary microscopy tools that allow us to both probe and manipulate topological states down to millikelvin temperatures. And one part of that research effort is to start to resolve electronic states layer by layer on van der Waals heterostructures. On the material side, we've also been developing methods to actually utilize the scanning probe tip to achieve in situ mechanical manipulation of the twist angle of Moré superlattices and twisted bilayer graphene and twisted TMDs. But in this talk, I primarily will be discussing this direction. So I'll start just by saying a few introductory words about the technique and operating principle of microwave impedance microscopy. And then I'll provide a few quick updates on our development of a new dilution refrigerator microscope that can open up some new gigahertz imaging capabilities in the millikelvin regime. So the previous talk already provided a very nice overview and introduction to the technique of microwave impedance microscopy. So I'm only going to provide a very quick overview here. So the microscope consists of a very sharp metal needle that we can scan over the surface of a material, and we can shine microwaves down to this tip via an impedance matching network, and then we can read out the real and imaginary parts of the reflected microwave signal. So on a qualitative level, this tip is generating very strong microwave frequency electric fields in a very small spatial vicinity right near the apex of the probe. And MIM is measuring the response of the sample to these high frequency electromagnetic fields from the tip. And if you're able to read out the real and imaginary parts of the reflected microwave signal simultaneously, one can get a lot of insight into the real space nature of conductivity and screening of various quantum materials. So as you can see in this picture, the tip is mounted on a tuning fork mechanical resonator. So this is a combined atomic force microscope and microwave impedance microscope. So basically what we can do is we can monitor the signal that's modulated at the tuning fork resonance and filter out signals at other frequencies. And simultaneously, we also use the tuning fork for continuous height feedback as well. So this is a very oversimplified cartoon level schematic of the measurement setup. So we can use gigahertz lock-in detection techniques to read out the real and imaginary parts of the reflected microwave signal. Because we're imaging in the near field limit, where the tip sample distance is much smaller than the frequency of the microwaves, it's very common to use lumped element models to characterize the tip sample interaction. The resulting microwave contrast can be illustrated in this pair of response curves. And the main takeaway message here is that the amplitude of the reflected real and imaginary microwave signal depends very strongly on the local conductivity of the material, which makes MIM a very useful probe for studying samples with spatially inhomogeneous conductivities or topological states. So in prior work, I've used the technique of microwave impedance microscopy to visualize chiral edge states at the boundary of a magnetic topological insulator in the quantum anomalous Hall regime. And in this case, the presence of the topological edge excitations is manifested in a very sharp enhancement of the microwave response at the boundary of the sample. So while this lumped element model that is shown up on the top of the screen works very, very well to predict the MIM response of conventional dielectrics and metals in a quantitative way, it starts to fall apart when trying to predict or understand the MIM response for more exotic quantum materials like topological insulators. So inspired by conversations with Alan McDonald on this data set here, one of my former students, Taiga, worked on developing a more general theoretical framework that could quantify the MIM response for more arbitrary quantum materials going beyond the lumped element model. And the main takeaway message of Taiga's work is that he was able to develop an expression for the MIM response within linear response theory that's given by this equation here. And to illustrate a concrete application of this model, Taiga used this to calculate the MIM response of an edge state in a Chern insulator. And the main takeaway message is that the strong enhancement of the microwave response that at the physical boundary of the sample could potentially be attributed to edge magnetoplasmon excitations, which are charge density fluctuations that propagate along the perimeter of the sample, and the resonance depends on the Chern number. So one of the exciting things about Taiga's result is that the expected experimental signature of edge magnetoplasmons is the appearance of a sequence of resonance peaks in the frequency domain or time domain, which could be picked up when the tip is positioned directly over an edge state. And this helps provide a very clear way of distinguishing topologically non-trivial states from topologically trivial states at the edge, or increased edge conductivity that's due to band bending or local doping or charge impurities at the edge. So in order to be able to experimentally access very low energy correlated and topological states. Over the past couple of years, my group has been working on trying to push the frontiers of microwave impedance microscopy into new ultra low temperature regimes approaching 50 millikelvin. So in order to do that, we integrated a microwave impedance microscope into a dilution refrigerator with a superconducting vector magnet. So as seen in this picture here, the scanning probe microscope and all of our cryogenic microwave electronics are mounted onto a top loading probe for fast sample exchange. And this picture on the right-hand side shows a close-up view of the microscope head and sample. And as you can see in the picture, the system is designed for simultaneous electronic transport measurements and microwave imaging. So you can use transport to assess the overall conductivity of a sample, and then use microwave impedance microscopy to gain some insight into the microscopic nature of electronic states in the sample. Okay, so in this experiment, we focused on performing layer-resolved microwave impedance microscopy in a van der Waals heterostructure with 2 conductive layers. So this is the simplest possible device structure that will allow us to start to do layer-resolved imaging. And a schematic of our measurement setup and our device is shown here on the slide. So this system was selected because it's probably one of the very simplest test systems for doing layer resolved imaging. And one of the goals or questions that we had was, can we use microwave imaging to disentangle or separate out the microwave signatures of electronic states that are sitting on the top layer versus the bottom layer at every lateral position across the sample, x, y. So while we demonstrated this with a double layer system, I would like to note that the concepts can be generalized to systems with larger numbers of layers. The data, of course, have become much more complicated, but in principle, those concepts should apply to more complex multi-layer heterostructures. So before I jump into our results, I would like to highlight a few key experiments that have been done already in the area of double layer electron systems. So one of the oldest and perhaps most impactful papers was this 1991 paper by Jim Eisenstein, where he demonstrated the ability to measure the electronic compressibility of a 2D electron system using field penetration measurements in a double layer device, as shown here. And this really set the foundation for a lot of future or modern experiments that are being performed in the 2D materials community on double layer graphene and other double layer devices that have been proposed to be platforms for an exciton condensate. In 2011, the group of Emmanuel Tutuk at UT Austin was able to replicate Eisenstein's experiments in double layer graphene. And what he was able to do was he was able to show that he could map out the Fermi energy of a graphene quantum Hall insulator using a parallel graphene sensor layer. More recently, there have been many groups in the scanning probe microscopy community that have started to use graphene sensor layers to facilitate imaging. So on the right-hand side is a paper, a very beautiful result that came out of Mike Promy's group at Berkeley a few years ago, in which he used a graphene sensor layer to do real space imaging of Wigner crystal states in a TMD hetero bilayer by measuring the real space charge density distribution on the graphene sensor. And more recently, Ali Yazdani's group at Princeton used a similar concept in which he used a graphene sensor layer to probe quantum Hall states in graphene and look at their interaction with charged impurities. Okay, so again, this is a schematic of the double layer device that we used. So the 2 graphene layers are independently contacted, and we have 2 main experimental tuning knobs. So the first is the backgate voltage, which can set the carrier density in both layers, as well as the interlayer bias, which also impacts both the chemical potential and carrier density on the 2 layers. So the simplest thing is to first consider what is the MIM response of just a simple graphene monolayer. And that result is shown here on the slide. So this is, I'm plotting here on imaginary parts of the MIM response as a function of gate voltage. And what you can see is a series of dips in the amplitude of the MIM of the reflected signal that correspond to incompressible quantum Hall states in the graphene sample. And this is data from my group, but similar results have also been obtained from other groups in the MIM community. So this is a system that's been really well understood and well characterized by now. And I'd also like to note that in this sample, we can also see breaking of spin and valley degeneracy near the charge neutrality point as well. Okay, so the next thing that we'd like to do is at least try to gain some intuition for what we would expect the MIM response to be of a double layer electron system. So first of all, one simplifying assumption that one could make is that the MIM response of the double layer system will primarily be dominated by the top layer, which is closest to the tip. So let's, for example, just for now, forget about the bottom layer or the reflected microwave signal from the bottom layer, and let's just consider what the MIM response of the top layer would be. So we just want to ask, how are the Landau levels in the top layer affected by Landau levels in the bottom layer? And there are two simple scenarios. So scenario one is that the lower layer is highly compressible or highly metallic. And what that means is that if you apply a modulation to the backgate, the electric field from this backgate will be completely screened by this metallic bottom layer, and therefore the top layer will not have a backgate dependence. So the other simple scenario one could consider is the opposite case, where the lower layer is fully gapped or fully insulating. And in this case, the electric field from the backgate should fully penetrate the bottom layer. And therefore, as you apply a modulation to the backgate, the top layer will see this voltage modulation, and you can basically shift the Fermi energy of the top gate with your backgate voltage. And this shift in Fermi energy can lead to a very large change in the impedance of the graphene sensor, which is detected by MIM, as you can see here in this data. Okay, so this slide here shows experimental data. So this is a plot of the MIM response of this double layer graphene system, plotted as a function of the backgate voltage and the interlayer bias. And at first glance, the MIM response appears to be dominated by Landau levels in the top layer. So the MIM dips that arise from incompressible states in the top layer are given by these purple horizontal stripes. So we want to track the evolution of these Landau level trajectories as a function of your top and bottom gate voltage to gain some insight into what's happening in the system. Okay, so the first observation from the data is that over most of this parameter space, the Landau levels in the top layer have a very weak backgate dependence. And this implies that the backgate is mostly screened by the bottom layer. And so under these circumstances where you see a very weak slope with respect to backgate, we would expect the bottom layer to be acting metallic or compressible. Okay, so observation number two is that we can also see that these regions of shallow slope are interrupted by very abrupt jumps in the Landau level trajectory, which I've marked here by these white arrows. And these jumps arise because the electric field from the backgate can penetrate the bottom layer and lead to a shift in the placement of the Landau levels in the top layer. So therefore, these white arrows correspond to conditions where the Fermi energy of the bottom layer is in the Landau level gap, meaning that it's incompressible. Okay, so that was just meant to give kind of a conceptual overview of what we would expect to see in this device. If you want to be more quantitative, you could write down a model that relates the chemical potential and carrier densities of the top and bottom layers to our two experimental tuning knobs, the interlayer bias and the backgate voltage, as well as geometric factors such as the capacitance to the two gates. All of this theory had been developed several years, I think maybe 30 years ago by Eisenstein. So if you'd like to look at the original derivation, you can check out his PRL from 1991. But the main takeaway message here is that the chemical potentials and the carrier densities on the top and bottom layer can be very quantitatively related to the voltage tuning knobs as follows. Okay, so if you take these, if you look at these two expressions and you consider the simple scenario where the carrier density on the top gate is 0, so we're going to set carrier density n sub t to 0. In this case, those two equations simplify to the following. And so the remarkable thing about this is that if you're able to follow the nu equals 0 Landau level and trace its trajectory in the gate-gate plane, one can experimentally read out the chemical potential of the lower layer. So what this means is that by tracking shifts in the Landau levels of the top layer, you can do a local electronic compressibility measurement of the lower layer. A side comment that I'll make is that the top graphene can also act like a top gate, so you can do local electronic compressibility measurements with displacement field control now. Okay, so the plot on the lower left is our experimental extraction of the chemical potential of monolayer graphene as a function of carrier density in the quantum Hall regime. And one of the nice things about using double layer graphene as a test system is that it's already been very well understood and characterized. And so we can extract the energy scales associated with the Landau levels in graphene and show that they match up with theoretical predictions. And this already provides some quantitative validation that this double layer model can correctly describe the system that we're looking at. Just going a step further, one can take this plot of chemical potential versus carrier density and then plot the inverse compressibility as a function of filling factor. And what we're seeing here is that we can resolve a full breaking of, we can resolve all of the broken symmetry states as well as the many of the fractions in monolayer graphene. So these dotted lines, the black thick lines refer to the integers and these dotted lines refer to the fractions. So basically, we're able to achieve detection of fractional quantum Hall states in the bottom layer, and we can also detect a negative compressibility in the bottom layer that arises from strong electron-electron interactions. And this field penetration sensing technique offers complementary insights that kind of go beyond what you would already get from conventional MIM imaging, because these compressibility measurements do give you some insight into negative compressibilities and the effects of electron-electron interactions. So I think taken together, both of these measurements can paint a fuller picture of the system that you're looking at. Okay, so as a second consistency check, we can model the MIM response of the combined double layer system. So in order to do that, we can basically model the sigma XX, or the longitudinal conductivity of the top and bottom layers, as a function of your two gate voltages. So the Landau level trajectories in the individual layers are shown here. And then one can use the conductivities on the top and bottom layer to model the MIM response in the combined double layer system. And the results of that simulation are shown right here. Okay, so one of the things that one might note from this theoretical plot is that it's possible to isolate the MIM response of just the bottom layer by imaging through the top gate when the top layer is incompressible. So we can do direct MIM imaging or direct MIM readout of Landau levels in the bottom graphene layer by imaging through the top layer. That is what we're showing here. So that was a theoretical plot. What do we see in the data? So we can resolve some dips in the MIM response that are shown as these vertical purple lines. And these dips are the incompressible peaks due to Landau levels in the lower layer. And if you take some cross-sectional line cuts through the incompressible state on the top layer, we can resolve nu equals 0, nu equals plus minus 1, and nu equals plus minus 2 in the bottom layer just through direct microwave readout. Okay, so with that as an introduction, so I've just showed how you can kind of independently disentangle the MIM signatures of the Landau levels in the top and bottom layers, and how you can kind of extract them from these two-dimensional gate sweeps. So the next question that we would want to ask is, so how is surface disorder on the heterostructure imprinted onto different atomic planes below the surface? So what we'd like to do is now use this Landau level tracking method to independently map out real space carrier density fluctuations or real space density fluctuations in the positions of the Landau levels on the top and bottom layers separately. And this allows us to create a map of electron hole puddles at different vertical distances down the throughout the heterostructure. So the procedure to do this is quite simple. So the first thing one can do is just read out the Landau levels in the top layer. And we know how to extract this from the gate sweeps. So the next thing that we can do is map out the position dependence of the density shift in the position of these Landau levels as a function of x and y. So the data that I'm showing on the top is just showing the carrier density fluctuations as a function of y, and then you could repeat this for many values of x. And then what you can get is a two-dimensional map of the charge inhomogeneity. So this gives you a direct visualization of electron hole puddles, which trace out the real space disorder landscape at different distances below the surface of the heterostructure. So we can go through the same exercise, this time directly doing subsurface imaging of Landau level shifts in the bottom layer, and then we can create a separate map over the same XY dimensions of carrier density fluctuations in the bottom layer as well. And one of the things that we noticed is that the geometry of the disorder potential on the surface layer is roughly imprinted onto the buried layer, but with a strongly attenuated amplitude. And to quantify this, we can plot histograms of the upper and lower carrier density distributions that can accompany each of these two-dimensional images. So if there are charge impurities or some sort of contamination on the surface of the material that introduces disorder, the effects of that disorder can propagate through different layers of the heterostructure in different ways. And that was one of the things that we were trying to get at with these images. Okay, so a natural follow-up question then is, what is the interplay between these fractional quantum Hall states and the disorder profile? And a follow-up question to that is it possible to actually tune the conductivities of different layers to tune the disorder potential in situ and change the visibility of fractional quantum Hall states? So in order to do that, basically what we did was we did subsurface imaging of the Landau levels in the bottom layer as we tuned the conductivity in the top layer. So it is possible to resolve quantum Hall states in the bottom layer even as you start moving away or tuning away from the fully incompressible state. So what we wanted to do is see what would happen if we started increasing the conductivity of the top layer, and we wanted to see if we could start screening out the surface disorder potential this way. Okay, and so the results are shown here. So basically, I'm showing a sequence of MIM plots. At the top, it corresponds to when the top layer is fully incompressible, and at the bottom, it's compressible. And we notice roughly three regimes of behavior, which I've labeled 1, 2, and 3 on the slide. So the first regime, which is highlighted here in yellow, basically this corresponds to a situation where the top layer is fully gapped, which means that there's probably no screening of the surface disorder, but we can easily image through the top layer, and we can observe prominent dips at U equals minus 1, 0, and 1 with excellent visibility. In the opposite scenario in regime 3, when the top layer is fully conductive, the overall visibility of the quantum Hall states is suppressed. And this likely happens because the highly compressible top layer is screening the microwave field from the tip, which reduces the contribution of the bottom layer to the overall MIM response. And interestingly, in an intermediate regime, we do see the emergence of fractions in the direct MIM response of the bottom layer, which is something that we did not see when just imaging through a fully incompressible top gate. So in an intermediate regime where the top layer is partially compressible, we start to resolve fractional fillings. And this likely arises because the moderately conductive top layer is screening surface disorder, but at the same time, it's just insulating enough to allow the MIM signal to penetrate through it. Okay, so I'd like to close with just a quick recap of some of the new sensing capabilities that are enabled by the double layer imaging. So basically what we can do is we can start performing local electronic compressibility measurements or MIM measurements with displacement field control. You could do either mode of imaging with displacement field control. And so right here, what I'm showing is the displacement field axis and the carrier density axis in the white arrows. One thing that I do want to note is that it's there are going to be modulations in the positions of these axes as the compressibility of the top and bottom, as the compressibility of the top gate is modulated. So it's not correct to just treat the top layer as a metal gate. Another thing that I'd like to mention is that this double layer geometry can be generalized. So you could replace the bottom graphene layer with any 2D system with some twisted molybdenum telluride, bilayer graphene, multi-layer graphene, and you could then basically perform some MIM measurements with displacement field control. And that was one of the original motivations behind this experiment, but I just wanted to mention this as one of the practical applications. And then finally, we do have a route towards tuning the screening environment within the heterostructure as well. Okay, so just to recap, over the past few years, we've been working on the development of a new microwave impedance microscopy system that works down to millikelvin temperatures. This is a fairly new development that we've just launched over the past 2 years. So it's still work in progress. I've also talked about moving towards layer resolved imaging in van der Waals heterostructures with multiple conductive layers and looking at how the disorder profile can be potentially propagate as vertically through the heterostructure and potentially be tuned. And then finally, one very active direction that I didn't have a chance to talk about is working on in situ manipulation of the twist angle of Moiré superlattices. And we're particularly interested in applying this technique to certain twisted TMD homobilayer systems. Okay, so I'd like to acknowledge the experimental team that contributed to this work. So the MIM experiments were conducted by Leonard Cao and Chen Wu. Liyuan Liu made the double layer graphene devices, and Qixuan was working on the Moiré rotor devices. And I'd also like to acknowledge some very productive theory discussions and collaborations with Taiga Wang, Dan Parker, Yizhuang Yu, and Zhurun Grover. So thanks for your attention.
Questions?
So listening to your talk, I had some random thought. Maybe you can tell me whether it's crazy or not. If you think about magic angle, mirror symmetric, trilayer graphene. No, that's a much better system than twisted bilayer graphene. But some of the physics is clouded by the existence of the Dirac cone, which appears in the mirror odd sector. And the mirror even sector is supposed to be like TBLG, right? But you don't see the correlated insulator equals 2 and things, presumably because of the Dirac cone. But if you can selectively image just the middle layer, right, that will be insensitive to the mirror odd sector. Maybe you'll see much cleaner resemblance to TBLG. Is that something that could work?
So that's a really interesting thought. These experiments rely on having the different layers independently contacted. I haven't thought very much about doing like layer resolved imaging in kind of a multi-layer graphene heterostructure. In principle, there would be a slightly different capacitive coupling to the gates depending on where the electrons are living vertically. But I think that for something that's as thin as like a twisted trilayer, it might be very difficult to resolve.
So two questions. One very basic. I'll start with what fields and were these measured at?
I think these were measured at 8 Tesla.
8, okay.
Yeah.
And two, I guess, conceptual question. So you showed how there was some similarity between the potential profiles that you were measuring, top layer and bottom layer from the disorder and from screening. Is it obvious, or is there a reason to expect that like most of the potential disorder is coming from the top? Is this because of how you fabricate these devices? There could be bubbles and weird things underneath too, or in the middle. I'm
Yeah.
just curious if you can comment more about that.
Yeah, that's a good question. So, I mean, so for the scanning probe microscopy, we select the flat regions of the flake to do the imaging, because if there's topography, it increases the chance of a tip crash. So there's definitely no bubbles in the part of the heterostructure that we're imaging. There are many sources of disorder or charge inhomogeneities, like you could have charge traps in the boron nitride anywhere in the heterostructure. There could be processing residues or something else sitting on the top surface of the sample. So I think that in our sample, it appears that the graphene layer closest to the surface is significantly more disordered, which implies that maybe there's a lot of surface disorder on the surface. I think anecdotally, this is consistent with observations from other transport groups. So it's kind of common knowledge that people can observe significantly cleaner transport, do significantly cleaner transport measurements in samples with a graphite top gate. And part of the role of the top gate is not just the displacement field axis, you're actually screening whatever junk or disorder is sitting on the surface of the device. So there's been anecdotal evidence that there's significantly higher quality and 2D materials that are dual gated with metallic gates. The problem with this is that for those of us that do scanning probe microscopy, we can't really take advantage of this. But this, using a graphene layer as a tunable screening gate, could potentially allow both, because one can image through it. And I assume that this is something that would work for scanning SCT as well.
Further questions? Thank Monica again. So tonight we're giving you dinner. It's gonna be at right on the floor.